Hello, and welcome to the ILP webinar series. I hope you and your families are doing well in these turbulent and uncertain times. My name is Irina Sigalovsky, and I am a program director at the MIT Office of Corporate Relations. Today, I'm going to be your host on behalf of MIT's Industrial Liaison Program. As you know, ILP serves as a gateway for connecting corporations with MIT and MIT-connected startups. MIT and ILP are open for business virtually. And today, I would like to welcome you to our first virtual conference, Autonomy 2020. Autonomy is already affecting our lives in many ways, but the effect is going to be much more profound going forward. You know, it occurred to me a few days ago that even though this conference is not about COVID-19, we will look at autonomous systems in a very different way when we come out of this crisis. Please note that the conference will take place over 4 days and will cover the following topics: autonomous vehicles, today's session, platform tech for autonomy tomorrow, presentations by 14 startups from the MIT Startup Exchange next Wednesday on April 15, and finally, autonomous manufacturing on April 16. More details of the program can be found on our website, ilp.mit.edu under Conferences tab. Today's session will feature presentations by 4 MIT faculty working on autonomous vehicles. Needless to say, autonomous transportation is a multidimensional topic. So today, we will only cover several aspects of it. What is clear is that this area is primed for a big change. But there is also a lot of unanswered and controversial opinions about when, how, and where autonomous vehicles will operate. So today's presentations will highlight the latest state-of-the-art research on this rapidly evolving topic. Before we move on to the presentations, I just wanted to tell you a few notes on logistics. At the bottom of your screen, you have several icons. Please use Q&A button to ask questions and also to vote on questions. Please do not use chat to ask questions. Chat is reserved for technical questions, such as if you are having problems with the platform. The session will be recorded, and recording will be available on our website. Finally, I apologize in advance for any technical glitches we might experience today. This is our first virtual conference, so we ask for your patience. With that, let me introduce our first speaker, Professor Sertaç Karaman. Professor Karaman is an associate professor in the MIT Air Astro Department and co-founder of Optimus Wright. His research interests lie in the broad areas of robotics, control theory. The application areas of his research include driverless cars, unmanned aerial vehicles, distributed aerial surveillance systems, air traffic control, certification and verification of control system software, as well as many others. Professor Karaman, please welcome.
Thank you so much for the kind introduction. It's my pleasure to be a part of this conference. And I look forward to telling you a few different things that we're doing in my research group. Today, I'd like to start talking about a few emerging technologies. In particular, I'll talk about autonomous social vehicles, autonomous super vehicles, and autonomous miniature vehicles. And if time allows, I'll talk a little bit about shifting opportunities in the business landscape. And I'll also talk about some of the teaching that we do using autonomous vehicles themselves. So let me get started, just dive into it and get started with autonomous social vehicles. Today, we actually have a lot of autonomous vehicles that are operating. We have autonomous vehicles operating on Mars, far, far away from Earth in a virtual world. And we have autonomous vehicles operating in very large warehouses in huge numbers. But the one thing that autonomous vehicles cannot do today is to operate in environments where humans are omnipresent and environments that are centered on humans. I believe that one of the biggest challenges that we'll face as roboticists, as people developing autonomous vehicles in the next few decades, will be to put autonomous vehicles in massive numbers in human-centered environments where humans are present, and environments that are actually built for humans rather than autonomous vehicles. We're doing a number of different things in this arena in order to introduce autonomous vehicles into human-centered environments. I'll just give you a quick example. One of the things that we're looking at is when autonomous vehicles encounter human-driven ones, how should they behave? For example, would you build an autonomous vehicle that cuts into every human driver, or would you build an autonomous vehicle that is extremely, extremely cautious and waits for every other autonomous vehicle to come forward? One of the things that we've looked at is to introduce something called social value orientation from social psychology. This is a metric that social psychologists utilize to measure how people behave. And in particular, they look at how people behave in terms of reward to themselves and how people behave in terms of reward to others. It turns out that looking at people's social behavior and psychological behavior, you can actually understand how people behave in different ways, and then you can engage with people in that manner. For example, if you find people who are more altruistic, they'll stop for you if you're an autonomous vehicle so that you can go. On the other hand, if you find people who are a little bit more egoistic, who try to maximize reward for themselves, they will not stop for you, so you'll have to wait for them in traffic if you wanted to get into the environment of an autonomous vehicle. We've been developing a number of algorithms and testing a number of strategies. For example, we've looked at different kinds of data sets to understand as the vehicles and an autonomous vehicle comes together, can we as an autonomous vehicle look at other human-driven vehicles and try to estimate on the fly whether they're going to allow us to merge or not in a highway. In other words, are they going to be altruistic or egoistic? And depending on that, we can cut in front of them or not. In particular, in this research, we've also looked at a large data set called the NGSIM data set. It includes a number of vehicles going on a highway. Using the algorithms that we've developed, we were able to identify the social value orientation of various vehicles driving in that highway. As you can imagine, vehicles that are merging in tend to be much more competitive than vehicles that are not merging in and waiting in the highway. This is a very deep research that we've engaged in, and we're doing a number of other things. I'll cut this part here, and I'll let you kind of reach out to me with questions if you have any. I'd like to end by saying that I believe this is one of the most important remaining items in enabling autonomous vehicles, to teach autonomous vehicles how to interact with human-driven ones or pedestrians or other types of humans on the road. And I believe it's one of the final challenges that we need to address before we actually get a chance to put autonomous vehicles on the road. The second part of my talk, I'm going to talk about what I call autonomous super vehicles. And these are vehicles that are much more capable than what human drivers are. Let me motivate this with autonomous flying vehicles. I don't know how many of you is familiar with what's called drone racing. This video may not be beaming at very high quality and high rate, but if you look at this video, what you'll be seeing is a drone flying in a very complex environment. The environment is shown from a camera mounted on the drone. This is called a drone racing event. In this event, there's a camera on the drone. The camera image is beamed back to an actual human pilot that's sitting remotely in another room and piloting this drone using a joypad remotely. And you can see the drone is able to fly in a very complex environment extremely fast. In these kinds of events, the drones reach about 80 miles an hour, sometimes even faster, going through these kinds of complicated environments. This kind of thing is just outright impossible today for autonomous vehicles to do. And humans can do a number of other things. For example, there's events that they can fly. Humans can fly them through complicated forest environments, and humans can even sort of fly drones to film, for example, things like racing events. And you can imagine if we were to be able to do the same things autonomously, we may be able to use drones in forest environments for search and rescue to find people who are lost, or to find people after disasters, for example. And if we can do the thing on the right, maybe we can kind of automate some of the events for the media. In my group, we focus on something that we call autonomous super vehicles. We try to develop robotic vehicles that are capable of navigating these kind of environments far, far faster than any human possibly can. As you can imagine, as humans, we have certain limitations in terms of, for example, how fast information can possibly travel through our neurons. Autonomous vehicles don't need to have those. This has a big impact on autonomous driving or driving in general as well. Here's a YouTube video that I put. It's showing a person trying to navigate through a highway and just barely misses an accident. It turns out that there's more than 30,000 people every year who die in traffic accidents just in the United States, and more than 1 million globally. And imagine taking all those fatal accidents right at the time of an accident, turning on an autonomous super vehicle, that can run cameras reaching up to 1 kilohertz, that can think far faster than any human, and can just nudge the car just so slightly that an autonomous, that if it's fatal accident became a near miss. For this purpose, we build a number of algorithms and hardware in my group. As you can imagine, the moment you start doing this kind of thing, the kind of webcams that you can find on the market or the kind of computers that you can find on the market are all extremely limited. For example, a typical webcam will run at 30 frames a second, sometimes 60, 80, or 90 frames a second. For this kind of thing, we need a kilohertz camera that can run at 1,000 frames a second. And typical computers that you get CPUs, even GPUs, are fairly limited. And so for this project, we use FPGAs and sometimes even FabR chips to make systems faster. In particular, we've been building a system currently in the form of a drone that has a 3D printed body. It has cameras that can go up to 1,000 frames a second. It has inertial measurements that are tactical grade, runs at 4 kilohertz. We even put odometry on the motors that I'll show you in a second. It can carry some other sensors too, and it uses FPGAs and GPUs at this point to do computing. In order to do that, we had to actually build our own circuit boards. So for people who are familiar there, we had in our group our own NVIDIA Jetson carrier. I believe it's one of the most advanced carrier boards out there for NVIDIA Jetson computers. It features a USB-C port, a PCIe connector. It has an IMU and CSI camera lanes, SD card interface, and much more. We've also built a 10-layer circuit board that carries FPGAs and DDR3 memory and connects the cameras using native high-rate camera lanes. And this board connects to the other one using the FPGA inside. I'll kind of show you what the system can do in a very few videos. And here you're seeing our drone flying in our motion capture laboratory. This is a large laboratory that we have at MIT. It's equipped with motion capture cameras. The drone seems to be doing some crazy motion, but what it's trying to do is to track trajectories as it's flying extremely fast. So these trajectories are being tracked at this point as the drone is going up to 30 miles an hour in this environment that measures barely up to 7 feet. And as it's doing that, it's introducing about 10 centimeter tracking error. And it's using some very high rate odometry on the wheels. And we can do a number of other things. For example, we can run the trajectories to be followed into a circle, and the drone will naturally sort of flip around to go through this. And here is one event that we've been considering. So you're going to see in a second the drone on the upper left corner as it emerges right here. And it'll race through a number of gates, turn around in a circle. It'll then flip around to pass the last gate, go very quickly into the final gate, and then finalize the turn. Of course, as you can imagine, building autonomous vehicles in this manner that can be extremely fast is actually quite challenging. One of the things that you face is you pull out these gates, you run your drone very fast, and you build this drone that has massive amounts of sensing and computing. It probably costs, if you build one by one, just like we do, more than $10,000. You hit one gate and you lose the drone. Not only is the $10,000 you lose, but you also lose sort of some time building the drone in. So one of the things that we've done is to build some sort of like a virtual reality environment for drones. What we do is we fly the drone in a motion capture room, take its position and orientation, run it through a game engine, and in this way, generate camera images for the drone and pass that back to the drone. So in this manner, the drone flies in a completely empty room, but if you will, it hallucinates a different environment that it's flying in. And it's very safe to fly in this environment. If you crash into an obstacle, that's just virtual. Nothing really happens. So you can rewind back and retry. We can also connect humans who are in a different room. They can be together present with the drone. And so we get a chance to do a number of different things like this by connecting a variety of environments, putting drones in, or even sometimes putting miniature vehicles and humans together, and we enlarge the vehicle so that humans and vehicles can be in the same space. Let me show you an example. So here is our drone flying in a warehouse environment. The environment is completely virtual. You can see the drone is actually flying in an empty space and hallucinating, if you will, this other environment in virtual reality. Here, one of my students is in a different room. He's just walking around, and the drone is going around this person to film him. They're in completely different environments, in different physical environments, but in the same virtual space. We do this by actually generating real environments into virtual ones. So we have pioneered in my group a technique called photogrammetry. We have pushed the limits of these techniques to get really high quality pictures and stitch them together. Here you're seeing a whole bunch of pictures taken of a real column, and this column is generated in 3D. As we rotate the column, you see a whole bunch of little rectangles. Those are the actual pictures in their localized versions. In this manner, we built a very large environment, sort of that makes up a warehouse. For this purpose, we've scanned 80 different objects, and we generated them in 3D, and we used 1,000 instances of these objects to generate this environment that you're seeing in. And that's where our drone was flying. I'll get back to this environment in a second. We've actually utilized this environment in an autonomous racing competition that was fully virtual, and then later we made that competition fully real. I'll get back to that in a second, but I'd like to let you know that although it's not just announced yet, I'm saying it publicly in here for the first time, we've been building a fully virtual version of 2 floors of MIT Study Center. MIT Study Center is, I would say one of the landmarks of Boston. It's a Frank Gehry designed building. It includes MIT's Computer Science for Artificial Intelligence Laboratory, as well as the Laboratory for Information Decision Systems, where a part of my lab is also located. So here I'm showing you a bunch of pictures. I didn't make this into a video so that you can see it. These pictures that you're seeing, these are not photos. These are actually renderings of what we can achieve in scanning these environments into virtual ones. These shots are from the basement of the building, and here are the shots from the first floor of the building. And so we're still building this environment. Once we build this environment, we'll be looking at a number of other things. For example, can we learn in virtual environments and transfer them to reality? If we can build virtual environments in this much of a realistic way. We will also be using this in some of our teaching efforts that I'm going to mention at the end of my presentation. I'd like to mention one thing before I continue to the next part of my presentation. Like I said earlier, building autonomous super vehicles is extremely challenging. And so I've been thinking pretty hard about engaging the rest of the community in doing this. And I've been working with the Drone Racing League, NVIDIA, and Lockheed Martin. We've announced a challenge that we call Alpha Pilot, and we were offering sort of $1 million for the bidding team. And we've participated in here as MIT, as one of the organizers of the challenge, to do a simulation version of the challenge. We have 500 teams interested in participating in the actual drone racing challenge, and my team built a simulator so that we can down select people once they build their solutions for a simulation challenge. And I'm just going to show you some of the videos of the simulation challenge. And so they race, all the people who participate, all these teams that I mentioned, race one by one. But I'm just putting their trajectories and how their drones navigate fully autonomously in the simulation environment all together. And as you can see, these are the top 20 teams in the challenge. And as you can see, they're doing pretty good once you're in the simulation challenge. Of course, there's a whole bunch of crashes that we've also observed as people try to go through the simulation environment. But in general, people have been doing extremely good in the simulation environments. I'd like to say that the simulation challenge, this is something that we've done back in March of 2019. We've invited these teams to MIT for the first time in June of 2019. And then we've done the real racing challenges with the real drones between October 2019 and December 2019. And I'm happy to announce that in December 2019, we've actually awarded to University of Delft in Netherlands $1 million prize after they've won the challenge. So next in my list, after talking about autonomous social vehicles, autonomous super vehicles, next in my list is autonomous miniature vehicles. And so when I talked about autonomous aerial vehicles, for example, a lot of people imagine vehicles of this size that you can hold in your hand, and maybe you can imagine them following you around, or they might be doing certain types of inspection and so on. But this is not as small as autonomous vehicles go, even though we call them micro aerial vehicles. There's vehicles that are this size that are called nano aerial vehicles. There are vehicles even that can fit on a bigger fingernail. It turns out that at this scale, motors become extremely inefficient, so it's much more efficient to flap your wings to fly. And if you look at this landscape, you're going to see that there's a big difference in size, and as you can imagine, there's a big difference in energy that's consumed in operating. For example, the vehicle that you can see in the upper right, the Pico aerial vehicle that's the size of a fingernail, takes only 100 milliwatts to lift itself and fly around. On the other hand, the typical kind of computers that we utilize, for example, the powerful CPUs and GPUs that fit on cars, could be as much as consuming power as much as 100 watts. Even the embedded GPUs that we utilize in building drones, for example, that are intelligent, they're about 10 watts. So you can imagine you need 10 watts or maybe 100 watts just to turn on and off some transistors so that you can understand your surroundings. Rather, it takes 100 milliwatts to lift itself. So what we have been doing is to actually design the computers required for these vehicles from the ground up. Not just design the algorithms, but design the computers and the algorithms, computing hardware and the algorithms together so that we can get to a scale where we can do similar intelligence that we see on drones or we imagine to be on autonomous vehicles today, but at a cost of, let's say, 100 milliwatts. This has a number of applications. I call them autonomous miniature vehicles. For example, you can imagine applications in little flying vehicles or little satellites. There's also applications in, you can imagine vehicles that can walk on water or vehicles that are soft robots or maybe even insect-sized ground robots. There's also opportunities not just in miniature vehicles, but maybe long endurance vehicles. So you can imagine, for example, blimps that can stay in the air maybe for a matter of like years. We've done a number of things in this domain, but one of the things that I'm going to introduce is we've actually developed a chip that consumes only 2 milliwatts on average when it's running at 30 frames a second, and 24 milliwatts on average when it's running at 170 frames a second. It measures 4 millimeters by 5 millimeters. It's fabricated on a 65 nanometer node, and it can run visual inertial odometry together with bundle adjustment in the back end. So you can imagine the kind of thing that this can do, as you're seeing on the other side, is that it detects a number of features on the camera image, and it tracks them. It then integrates that tracking information with an inertial measurement information in order to find the position and the ego motion of the camera, IMU, and the chip system with respect to its starting point. As you can imagine, these kinds of technologies are extremely useful for both miniature vehicles, as well as for example, doing virtual reality, augmented reality devices, or similar technologies, for instance, on your smartphone. There's a number of other opportunities in this direction. For example, not just visual inertial localization, but we've been looking at how we can do depth sensing. Imagine taking a camera input and generating a depth image so that you can understand where the obstacles are. We've been looking at computing in a exploration task where the next best places to go. There's even some very interesting, challenging, and intellectually stimulating problems in decision-making and planning. For example, if you try to plan a path that reduces the energy consumption for actuation, for example, your fuel consumption or your battery consumption as you fly, if you try to think very hard in planning this trajectory, you may find one that, as you execute, expands very little battery, but you just spent so much energy in computing this path. And so in some sense, you need to balance out how much energy you expend in computing a path and how much energy you expend in actually executing it. And so there's some very interesting problems at this intersection of circuits and robotics where we look at low energy systems. I'd like to say that all of this work this autonomous miniature vehicles work is joint work with Viviane Zeh, who also has a talk in this Autonomy conference tomorrow at 11:55 a.m. She'll go into much more detail on autonomous miniature vehicles, as well as her own work looking at AI. So if you're more interested in this part of the work, please tune in at 11:55 a.m. tomorrow. Finally, I'd like to get to some of the shifting opportunities on autonomous vehicles and a little bit talk about my company, Optimus Ride. My experience in autonomous vehicles actually goes all the way back to the Dr. Urban Challenge when I was a part of MIT's Dr. Urban Challenge team back in 2007, working on the control systems. And back from then, in 2007, all the way to 2014, I would say, when this prototype by Google was introduced, many people believed that fully autonomous vehicles, where you can buy maybe your vehicle and hit that button and it drives itself fully autonomously, is just around the corner. Many people have predicted it's just 2 years away, all the way from 2012 to maybe up to 2017. But more recently, it's becoming clear that this kind of technology is extremely hard to develop. And we've been saying similar things since 2014. So there's so many things that makes it hard, but if you think about what are some of the things that makes it hard, I would introduce two axes. One is the speed of the autonomous vehicle, and the other one is the complexity of the environment. you can imagine as speed and complexity increase both at the same time. For example, if you look at fully autonomous driving under all conditions, in all scenarios, that is extremely hard, and I think that's going to take a long time. However, I should note that there's some medium-term or near-term opportunities, for example, in high-speed, low-complexity environments. Maybe we can automate highways. Or maybe in low-speed but high-complexity environments, for example, driving on dedicated lanes. One of the things that we've looked at is medium-speed, medium-complexity environments. So you can imagine, for example, geofence locations. They could be parks, university campuses, airports, and so on. And I believe that the opportunity here is much closer. So I'll briefly talk about Optimus Ride. It's a company that we've incorporated now about almost 5 years ago in 2015. And the company works on building autonomous vehicles, self-driving vehicles in geofenced environments. And so in this company, we imagine kind of systems that can operate at medium speed and medium complexity environments without any driver whatsoever. And also we imagine these kinds of systems being empowered by, for example, people in the background who can call into the vehicles, who can change sort of where the vehicles are headed in real time. But the key opportunity here is for a small number of people, small team of people, to operate a large fleet of vehicles to unlock the economics. And if you're interested in this more, one of my co-founders, Ryan Chin, is going to also talk about the Autonomy Conference at the Autonomy Conference. His talk is in exactly a week from now on Wednesday, April 15th in 10:05 a.m. And he's going to talk about a number of different things that we're doing. And in this picture, you can see 4 of my other co-founders together with Ryan. Finally, I'd like to spend the last few minutes on sort of teaching with autonomous vehicles, and then I'll kind of take some questions. I would say that as we develop autonomous vehicles, I've been observing a number of opportunities in teaching with them as well, and I'd like to share them with you a little bit. I've been working for the last, since 2016, a program, a high school program called the MIT BeaverWorks Summer Institute. And this program started in 2016 with this video that you're seeing as a summer program for high school students. It was a spin-off from my undergraduate robotics class at MIT called Robotics Science and Systems. For that class, we had developed these little miniature cars that you're seeing. And for the first time, we kind of gave it to high school students so that they can develop fully autonomous software that makes these vehicles, little vehicles, fully autonomous, so that they can understand AI, they can understand robotics, and they can get excited, and we can kind of embed them into STEM fields. We started the program in 2016 through the MIT BeaverWorks initiative, which is an initiative between the MIT School of Engineering and the MIT Lincoln Laboratory. And I kind of spun off for the first time my class as an autonomous race car Grand Prix. And these are the students that we attracted at that time. There were 46 students coming from all around the United States. So this was in 2016. In 2017, we actually grew it into 2 more courses, and these courses were, one of them was inspired by the other undergraduate course that I teach at MIT, so we introduced that as autonomous air vehicle racing. We attracted, in this case, 100 students who came to MIT as residential students, spent 4 weeks at MIT, and we also, prior to that, had 300 students online who would take an online class during the spring semester. And in 2018, we grew this to 200 students who spent 4 weeks at MIT, taking one of the 8 courses in this time. And admittedly, at this point, I wasn't able to, of course, teach 8 courses, but we had a whole bunch of staff, about 80 people helping out from MIT Lincoln Laboratory from a number of different fields. At this point, we grew the program, not just the autonomous racing, although the autonomous racing part was about 1/3 of the program and was the flagship course. But we had a number of courses in emerging technologies, for example, all the way from building a CubeSat to building a 3D printer. And just last summer in 2019, we grew it to 250 students who visited campus for 4 weeks in the summer of 2019. And we had about 1,000 students online taking one of 10 courses. And we're still continuing the development. Given the situation this summer, we're actually virtualizing a number of our courses. And in particular, last year, we've also kind of started a middle school program. So here you're seeing a bunch of middle school students, a little bit to my surprise. Middle school students have been quite different, admittedly, than high school students. High school students are a lot more closer to the freshmen, for example, the first-year students that we get at MIT. But middle school students are a very different kind of set of people, I believe. a lot more challenging, a lot more fun, a lot more rewarding at the same time. And so we started our summer program for middle school students in 2019 for the first time. And in the fall semester of 2019, we actually have done an all-girls program, both for middle school students and high school students, which we repeated a number of times. And now what we're doing is, first of all, we're building an important development environment that allows students to learn using autonomous vehicles in extremely realistic sort of racing environments that they can just kind of use their laptops, connect to some cloud computing resources, and beam the information back. We're also building a number of reference platforms. So we're building these kinds of things into a toy, you can imagine, and you buy it, you open the box, comes out an autonomous little vehicle. We have a number of versions that'll be ranging all the way from $500 to $5,000, and you can put some of the algorithms, for example, that you can do things like imitation learning, reinforcement learning, or you can do some model-based algorithms to program them, and you can build them. So this will be on the market pretty soon. We're also building a large platform for hands-on online learning, so that students can tune in and try out a bunch of different kinds of classes on their own. They can learn in that way, and then we're also kind of making this into a bit of like, imagine like an app store, whereby people can put their own courses running on the same sort of vehicles and same sort of development environments. With that, I hit the 30-minute mark, and if there are any questions, I'll take those. Thank you so much for listening.
Sertaç, thank you so much. It's always been mind-boggling to me how many different projects you're working on. So we have a lot of good questions here. So let's start with the first one. Professor Karaman, do you see your first topic as bridging the gap while there are non-autonomous vehicles out there? I see this topic as a temporary fix until most vehicles are autonomous. Since then, they can just all talk to each other and give their state. Your thoughts?
Yeah, I do. I do agree with some of that vision. I think that there's a lot of things that we talk about regarding autonomous vehicles, and I think it's a little bit of just a matter of timelines and maybe getting these things right. I can see that there will be some environments where it'll be just fully autonomous vehicles altogether. But even in the long run, I don't see. I think there will be some places in autonomous vehicles. For example, there may be autonomous delivery vehicles that are just kind of going on around the sidewalk for, let's say, the foreseeable future. And even autonomous transport vehicles that are running on sort of completely automated roads, it may happen one day, but it's just really hard to understand what the timelines for that can be. It's possible that it's 5 years ahead. Maybe that will be too optimistic, but it could very well be 50 or 100 years away. And so in the meantime, I think there's a lot of opportunities in autonomous vehicles that I think we need to take a look at. And I think they will introduce, I would say, unlock tremendous business opportunities. And to me, it's very clear that many of those opportunities will be in environments where humans are omnipresent.
Maybe connecting to this last question, where do you see this field in 3 years from now?
That's a great question. And so I think in 3 years from now, I imagine still a lot of development in many areas. But let's say between 3 to 7 years from now, I think I can see a number of autonomous vehicles in a variety of different environments. In fact, if you back up a little bit, I think that whenever sort of new technologies come in, I think we try to look at those technologies in what we know. For example, the AI technology comes in or the robotics comes in and we know about cars. And so what we expect naturally would be, we expect that one day we're going to buy a car and hit an autonomy button and it's just going to drive itself fully autonomously. And we did expect that from 2010 to 2015, I would say. But I do think what might happen in the next 5 to 7 years or 3 to 7 years is that we might see autonomous vehicles mushroom in a whole bunch of different fields that we wouldn't expect. We might see them in warehouse environments. We might see them in, for example, parks or resorts. We might see them in sidewalks doing deliveries. And in much of these kinds of applications, I think one of the things that may also happen is that we might realize that even though there's no driver on the seat, there might be a lot of people who are actually managing these vehicles back in control rooms. And I do think that the economics would still be unlocked if, for example, you have a small team of people managing a large fleet of vehicles. So that means that in a lot of the cases, these vehicles will be just kind of going through an environment alone on their own. But at the same time, when they're in trouble, when they get stuck, they can put themselves in a safe situation, and a human operator remotely can get them unstuck. And you can imagine that this could be, for example, in environments like, you can imagine malls maybe, where you can have security vehicles that are sort of going around, or vehicles that can show people where to go next. You can imagine vehicles on the sidewalks that are doing deliveries. You can imagine vehicles that are going maybe a little bit more slowly, if not 3 miles an hour, maybe 20 miles an hour in geofenced environments, and many more that I think that we can see, that I believe we'll start seeing slowly in the next 3 to 7 years.
That's great and fascinating too. Next question. In a mixed human autonomous driver world, which will likely be in place for many years, how would an AV handle a busy four-way stop sign intersection where there are many aggressive humans? More generally, how will AVs handle the mixed driver world when the humans know the AVs will always yield?
I'd say that's an excellent question. And so when I was preparing this talk, I actually do have a lot of other work in my group that looks at not just the technology, but a number of other things that relate to technology, like going all the way from, for example, opportunities in business, to policy, to societal issues, to maybe even planning and architecture, like urban planning and architecture. And I do think that these kinds of issues are as important as building the technology for autonomous vehicles. And I do think that we're going to face them pretty soon, pretty rapidly. And so one of the things that you mentioned, for example, if you have an autonomous vehicle that's navigating to a place, especially if it's fully empty, a lot of people may kind of view it as a machine, and they may really abuse it. If it's you kind of have like a fully empty vehicle coming from the other side, you may feel like, well, it will stop for you anyway. So you can just start cutting in front of it. You can start maybe not allowing it to go to places it needs to go. And even if it doesn't undermine safety, which I'm sure it will, but even if it doesn't undermine safety, it will undermine its efficiency. So I think one of the important issues that we'll be facing pretty soon, pretty rapidly, will be, how do we operate these kinds of vehicles in this societal and social environment? Are there any policy implications? And what are some of the ethical implications even in these types of environments? So I didn't get a chance to go through this at all, but I do think that there's quite a bit of awareness already in this field, and there's some research going on. One thing that I can mention, for example, just to give an example, is that, when we have people that we interact with ourselves in a social environment, like, for example, if you're interacting with a person face-to-face, sitting around the table, you're much more likely to be, let's say, quote unquote, nicer to them. But if you're separated from people who are, let's say, you're on the internet and just typing some YouTube comments, admittedly, people on large scales become pretty nasty. And so you can imagine, if we don't have anybody whatsoever monitoring these vehicles and maybe operating their behavior and able to communicate with other drivers, yes, people, when they're at a large scale, they may really kind of abuse these vehicles. But there may be some solutions in embedding some humans into how these vehicles behave. There's a number of research groups, for example, that are looking at, how can we actually convey that there's a remote operator behind this vehicle when the vehicle's efficiency really goes lower. And so then human operators, or other human drivers, would know that there's another human operator that we're really interfacing with, at least at this time, not just an autonomous vehicle. I'll just cut it there. I think that, we could talk about just this one topic for a long time, but I appreciate somebody actually flagging that this is not just about technology, but there's a number of other issues that we need to think about.
Switching gears a little bit. Let's see, how 5G technology can influence the development of autonomous vehicles?
This is another really excellent question. And so, like I said earlier before, I think that there's some opportunities in a small number of humans helping out autonomous vehicles as they navigate. And this is especially, I think, key, for example, if you imagine autonomous vehicles like little robots that guide you around in a mall, or autonomous vehicles that are navigating very slowly on a sidewalk to deliver your packages, and maybe even autonomous vehicles that are navigating at medium speed in let's say, geofenced environments. And in order for these types of people to connect the autonomous vehicles, we will need networks that have to be wireless clearly, where, we can kind of have some guarantees on bandwidth, as well as guarantees on latency. And so I imagine that as we develop the 5G infrastructure, these kinds of opportunities will be a lot more clear to people. And not to mention, there's also opportunities in, for example, embedding sensors in infrastructure. So for instance, an autonomous vehicle approaches an intersection. Even a human-driven vehicle can approach an intersection, and you may not be able to see around the corner. You can imagine there could be a sensor, just a camera and a computer on a traffic light, and they can show you what's around the corner. They can probably take that camera image, they can process it and give you, if they had the right kind of opportunities to communicate, they would give you the data that you need. And as we develop these kinds of networks and as they become reliable, I can imagine sort of humans communicating with these kinds of vehicles and the vehicles communicating with each other and the vehicles communicating with infrastructure. I still do think that even though there's a lot of research, I think for it to be recognized in the business opportunity, I think we will first have to build these 5G networks, and then we'll have to build the standards that make them really reliable, as we talked about. And then I think we'll need to gain some trust into these systems. We'll need to know that they're actually working before we kind of completely start relying on them. But I do see that in the next 3 to 7 years, 5G types of networks really contributing to what we do in autonomous vehicles.
Sertaç, thank you so much. Unfortunately, we have to stop there, even though there are many great questions. Thank you so much. And we're moving to our next speaker, Dr. Brian Reamer, who is a research scientist in the MIT Center for Transportation and Logistics. He's also a researcher in the MIT Age Lab. And the associate director of the New England University Transportation Center at MIT. Brian's research seeks to develop theoretical and applied insight into driver behavior. He founded and leads 3 academic partnerships with industry. For example, the Advanced Human Factors Evaluator for Attentional Demand Consortium aims to develop the next generation of driver attention measurement tools. Dr. Reamer will talk about automated vehicles, the current landscape, and the view forward. Brian, over to you.
Thank you, Irina, and thank you very much, Sertaç, for a great introduction. I'm a strong believer that the future is one of highly automated vehicles, and our pathway there may be much longer than many would like to predict. Since the early days of autonomy, nearly 100 years ago, we have had a quest to move the driver out of the driver's seat into either a remote control situation, which we see and we talked about in Sertaç's earlier talk, or out of the vehicle completely. So if you do a quick Google search, the first experiment with autonomy was really back nearly a century ago. 50, 60 years ago, GM invested a fortune in the topic for the time. The context of autopilot, for instance, is elegantly shared in some YouTube clips that GM had as advertisements at the time. In the early 80s, several prototypes. The DARPA Urban Challenge, where we aimed from an academic industry partnership perspective to begin to develop robots that tried to navigate the early 2000s. In 2009, let's call it, the modern era of self-driving was launched by Google's quest to change how we live and move. And at the time, technology that was forecasted to impact us in 5 years or less. In the 10 years since that time, numbers upwards of $16 billion have been spent on highly automated vehicles and countless more on technologies to support that and evolve automation into consumer vehicles. So as we look to the next century or more, what's next? And I, for one, do not see the small-scale deployment of automation a considerable investment to be success. How do we transform how we live and move with the support of technology so that there is a business case to move society forward in convenient and productive ways? So one of the key problems here is when we begin to talk about autonomy, it means different things to different people. As I talked about in 2018 in my Forbes blog, when we think about what autonomy perspectives are, everybody has a different answer. For those focused on level 4 and level 5 automated systems, it's all about seamless mobility without a human involved. To many of us, aspects of hands-free driving. To others, policy in particular, intermodal connectivity. It's all about getting people to steel-on-steel rail or buses or other convenient mobility services and getting them off the roads. To me, how do we build a mobility solution that moves safety towards a targeted threshold that is much more strategic? Where beyond the current crisis, one of the society's biggest quests is how to deal with the global health crisis that's on our world's roads, where 1.4 million or 1.4 million globally die a year. So how do we begin to think about bringing definition to the key problem in our quest? What are we trying to solve? Is it just packages? Is it people? Is it safe mobility for all? So one of the harder pieces is that when we look at consumers in particular, and we talk to individuals in some of our survey work, that we talk about levels of automation. We talk about the complexity of whether the human is involved as a teleoperator, whether they're involved to recover and drive through an intersection. One of the complexities is when you go to an average individual on the street, all we really understand is, am I driving or am I riding? And from a foundational terminology perspective, whether we're engineers or communicators in the media, we need to begin to focus on the fact that consumers who are expected to benefit from these technologies, by and large, don't know what we're talking about. That means consumers are expecting around the corner technologies that are going to automatically take them to the doctor's office, drive their kids to school, or do other things conveniently for them. And that may very well be the distant horizon. But riding, or a child riding in the back seat of an automated vehicle, is something that is several decades at best from changing how we get our kids to school. So moving that communication forward from these definitions and really beginning the education pipeline, because one of the myths about automation is that we need less human expertise. We need to actually educate people along the way on how this changes occur and set that reality gap and reduce that reality gap. So a number of years ago, now in its 5th year, I formed the Advanced Vehicle Technologies Consortium at MIT, which is now supported by about 17 different automotive stakeholders, from manufacturers such as Toyota and Jaguar Land Rover, Audi and Volvo, to safety suppliers such as Aptiv, Veoneer, Lear, Google, as well as other key safety stakeholders, to begin to look at how people are using advanced driver assistance systems, early stage automation, automated driving features such as autopilot, super cruise, pilot assist, and other related technologies in production vehicles on roads today. How do we look under the cover at how people are beginning to leverage technology to help inform and build better educated guesses as how to innovate forward tomorrow? So a lot of the world in autonomy has looked to the far reaches of what may be possible 10, 20, or 30 years in the distance. I, for one, believe there's a lot that we can learn from looking at what's occurring today to iteratively move faster in changing the safety landscape on the road today and getting technology from the classroom, from the laboratory, into people's hands to improve mobility decisions. So how do people adapt to these technologies? How do they use them or avoid using them to begin to leverage technology more strategically as part of our lives? One of the things that we quickly realized that there is a huge data gap. There is much projected benefit of technology in cars, and the product forecasters do a great job of saying, how good can this system be? Unfortunately, in the complexities of real-world life, crash data and claims data from the insurance industry will tell you that these systems are far less effective on average than projections. ABS is a great illustration. We presume that ABS systems would reduce crashes. The insurance data proved a number of years later that that wasn't the case. Electronic stability control was the additive features that really showed the benefits of ABS braking systems. So as part of ADT, as we begin to look at these problems, there's a number of things that we begin to very quickly understand. That many of the developments of advanced driver assistance systems and automated driving systems are really built upon a set of conditional operating characteristics. Operational characteristics that engineers have designed for engineering systems. No mystery, we as engineers need specifications. Unfortunately, those specifications are not well understood by the consumer. So drivers don't necessarily have the skills required to leverage these technologies. How many of you on the webinar here today have purchased a newer vehicle and can't quite figure out how the anti-lock braking systems, lane keeping systems, forward collision alert systems are all there to support you, let alone the automated driving features? Many systems require driver management oversight beyond the capabilities of human attention alone. Technologists building these systems often assume that we as humans will behave ideally. As Dan Ariely's book points best, we as humans are predictably irrational. Who would truly pick up a cell phone while they're driving down the road if they were truly concerned about getting from point A to point B safely? And finally, our infrastructure is far less than ideal. You know, potholes and high technology do not mix, let alone the weather complexities that we observe here in New England and other places of the globe. So it's not saying that past research in automated driving systems and advanced driver systems is wrong. It's just limited in scope in comparison to how real people are beginning to touch these technologies as part of real life. So how do we iterate forward from here? So in the video here, we can see an individual driving in one of our equipped vehicles here with autopilot, you know, fidgeting with something in their lap, reacting to emergent changes in the roadway environment. Who would expect that an individual here is going to attend to the world around them when the driving responsibilities are no longer there? Perhaps it's the salient looming effects of what's going on around us, but what's going on our nation's roads and the changes in risks and the fatality numbers are really predictable based upon some of the technology changes that we see. GM Super Cruise, on the other hand, has a driver management system. We can watch the hands kind of melt away from the steering wheel during an individual's first use of the automated driving feature. Convenient, intuitive, comforting. And I think GM Super Cruise feature is really an important system, not because of the automation itself. The automation is good for a first generation system, but it's the innovative driver management system that is really critical. So when much of the technology world looks at the automation here, they say, hey, it's not really that good. Well, it isn't. It's not aiming to be a level 4 or level 5 automated system. It's aiming to be a system that includes the human as part of the decision loop, leveraging human expertise when it makes sense and machine intelligence combined together, fused together, much as the aviation industry has long proved since the early 80s was the key to cockpit safety. So a couple features of the GM system. We begin to move from level 0 or manual control to level 1 or assisted driving, ACC, automated cruise control, over to level 2 or lateral control and distance control together. It's the transition harmony between these states that allows people to learn effectively and begin to leverage these systems. We are not born with the skills to understand how to work with autonomy. We need to build them. And it is an intuitive design of these systems that it's key that we begin to learn about the pathways to these technologies. So if we look at a couple of the key features within the system, you know, call it the blue state that GM has designed in here, an override state. I'm not comfortable with what the automation is doing. I want to pass a car. I want to change lanes, allowing the human supervisory control. The key here with Super Cruise is that there's a driver management system that only allows you to look away from the road for up to 6 seconds. We need drivers relatively attentive with the brittle automation that exists today. So again, the key, allowing us to supervise the automation simply and seamlessly, and the automation to resume control when it can. Let's call it the red state, where the automation has exceeded its operational bounds and it is looking for the driver to take control imminently. The alarm I'm not playing here, obviously cueing an individual's attention, changes in the illumination in the instrument cluster, something is wrong. So in the case here, in stop and go traffic, the automation looking for the human to support it. Well, much has been said about the fact that perhaps humans are terrible overseers of automated systems. They are. But can we use technology to support the human and include them to be better overseers? And the aviation community, as I mentioned earlier, has really done that since the early 80s. That has led to the advances in aviation safety. There's a reason that there are pilots still in many commercial aircraft. They're there when things go drastically wrong to try to help. The key is ensuring that they don't touch the technology when they shouldn't. So automation in and of itself, ACC in this case, distance control, increases monitoring costs. We look at things more. In essence, by some definitions, automation creating a distraction in the vehicle, distracting attention away from the roadway, looking at the instrument cluster for more information. So as we shift from traditional drivers to modern drivers with technology supporting us, our roles as drivers is changing. No mystery that the cab of a vehicle looks more like a cockpit with dials and knobs today than it did a few years ago. How do we begin to ensure that we can connect the human more seamlessly to this technology? So can a driver maintain sustained attention? Not really. It's much more of a two-way street. And in the lab and the team, thinking much more about how we develop and enhance two-way collaboration between the human and the automation. Mutual support, allowing the automation to understand, is the driver there as a backup? Allowing the driver to more informative understand how to build and where to build trust in the automation. It's all a two-way street. And in some sense, by many definitions, and Google talked about this in the early days of their self-driving car program, is developing this two-way street is as complex, if not more complex, than developing the automation features in and of themselves. The key is, though, is that we are transitioning from a human-driven model where our trust in technology and our comfort in the ethics of robot decision-making hasn't been fully formed, to a future of automation, as opposed to revolutionarily moving people out of the driving role. So when we look to the future, we need to be more focused on successfully developing collaboration between the robot and the human. Whether that collaboration is from a driver in the driver's seat or a teleoperator that's going to need to step in and ensure that those who are in the cab of the vehicle are comforting and trusting in the situation. So when we look to the future, much like the aviation industry has harped on, drivers have a role in the successful deployment of automation. Much of the L4, L5 community is focused very much and very core in the technology, which may very well make sense. But when we look to the future, we need to look to harmonizing the role of supervision. Where and when can we monitor, manage, and motivate drivers or operators so that we encourage safe operation and more convenient mobility? This isn't new. Automation-enabled vehicle systems have delivered on improved safety. As I mentioned earlier, electronic stability control. We believe strongly that automatic emergency braking will have significant impact on safety. Driver attention and related awareness may be at historic lows. Everybody who's not driving quite as much right now, roads are safer than they've been in decades. When you are out there driving or walking, watching how inattentive folks are around us. Well, it's not just drivers, it's even folks walking across the sidewalk in Cambridge, focused on their smart technologies around them. So increased automation really needs to be coupled with increased comfort, mobility, and safety. It's really a little carrot and stick here. What do we want? We want comfort. We want increased mobility. We want safety. And some of the sticks we can use are motivating individuals to behave in a more compliant manner so that we can collaborate. So collaboration, monitoring, and readiness to take over in extreme conditions that move outside of the domain at which engineers can build systems is really critical today. It's no mystery that new interfaces are going to be needed. It's really a communication issue. How do we develop systems that monitor, manage, and motivate drivers here? It's all about using new research and new innovations in infotainment, communication, and context-related integration. Whether that's a heads-up display or a full windshield display is an open question of the future. And I think many of the traditional manufacturers and suppliers are investing in these areas, but perhaps they've been a little distracted in the $16 billion quest for pure self-driving, where we need stepping stones on our way to get there. So as part of this, we really need to, in one sense, be thinking more deeply around human-centered considerations of attention management. We've been focused for so long on trying to get the distraction out of the car, the smartphone, the cell phone conversation. Perhaps what we've been missing is those technologies are being brought into the car because driving in and of itself is boring most of the time. It's not attentive enough. We don't need to attend to the road all the time because nothing's happening out there. As we automate more, no mystery, less attention is required most of the time. But in the rare instances where something goes wrong, how do we ensure that we're redirecting attention most efficiently? The Yerkes-Dodson law of arousal suggests that perhaps we need to be calming and relaxing drivers when they're overloaded, overstressed, and over-distracted by secondary activities. But we need to be alerting them and promoting reasonable attention strategies when they're not. So perhaps this is a very complex mix of how do we solve distracted, drowsy technology influx driving along the context together. And we believe strongly in the lab that we can do this with the aid of automation, supporting drivers effectively. So when we look to the advances in HMI that are going to be critical to supporting drivers and riders, is really new display contexts. How do we ensure that drivers are aware of the mode that the vehicle is operating in, that they are aware of what's occurring around them, and they are aware of the operational relevance to different information? When is it critical to be alert and ready to take over? When is it okay to relax a little more? One of our partners, Lear's Learning Intelligent Vehicle concept, is a core illustration of how you bring context-aware computing to production-level vehicle systems. More effective multimodal interfaces, how do we use haptics, auditory cues, visual displays more seamlessly together to ensure the elevated alerting? How do we develop more into innovative external HMIs so that the pedestrians moving through a crowded intersection around drivers are alert and aware of the likely activities of a vehicle? Perhaps this is also an important aspect where we think about salient advertising space, because by and large, as we are driving less, the advertising potential of both the interior and exterior of the vehicle is going to change. Integrating this communication, infotainment, and safety systems through synergistic interfaces is really critical to the automated and connected mobility system we all seek. This isn't about building technology for technology's sake. This is building technologies so that we can find new pathways to enable safe mobility and resources and the development of products people want in their homes. Defining success here is going to be far more than getting a robot on the road delivering groceries. It's far more than a technological competence to build better LiDAR, radar, more cheaper, more effectively. Consumer perceptions, experience, the cost of buying this technology even in your own car or renting it and sharing it in an Uber. Federal, state, and local policies are probably going to be the governing factors here. How do we enable leadership so that the organizations working here see a pathway to success over decades? Our federal government here in the United States has not been providing strong leadership. We need to be thinking about how do we ensure that folks aren't driving in a straight road. I'm not sure I'm concerned about which lane of the interstate they're on, but they're all moving in the same direction. That when something happens that goes wrong, we have the policies and procedures that we don't repeat the Uber accident of several years ago. How do we begin to look at the infrastructure requirements? We talked about 5G earlier. How do we ensure that the roads are paved effectively so that robots can effectively navigate? how safety these systems truly need to be. The ethics of autonomy is a complex Pandora's box. For me, I believe that if we can move safety effectively from where we are today, iteratively forward, we're making good progress. Could we set a standard looking for a 5% reduction in global fatalities in a set year, 10% after, 15 beyond? In some sense, technology agnostic. Doesn't matter how we get there. The key is that we are moving toward a safer mobility ecosystem. So how these pieces come together is really going to define the success of our mobility system and how autonomy can impact how we live and move. It's no mystery that the current economic climate is going to slow investment here. How do we encourage the strategic targeted investments so that we see success in autonomy in a business context over the coming decades? I, for one, believe the policy pieces are critical. It's all about paving the roads effectively so that we can see less risk in investment. Today, in the US in particular, there's a fractured relationship between the public and private sectors in mobility. How do we get the public sector and the private sector working more seamlessly together? The private sector needs an understanding of what the frameworks for success are going to be. The expertise in technology, in insight and understanding is not, however, in the public sector. The private sector needs to talk about a little more of what do we need the roads paved like? How do we need to paint the road lines? I, for one, believe we need to take a much more overseeing public health perspective on the risk benefit of safety. I talked about this in a TEDx talk nearly 2 years ago. This is a health crisis. We need to look at innovations that move that risk benefit curve forward in productive ways and endorse them. And we need to limit those that increase risk. That means we do need to test on public roads, but we need to test much more strategically than many states allow today. We need to look beyond engineering standards, where SAE builds a standard and everybody races towards that standard, to continual process improvement. As we look at low-level and high-level autonomy as it exists today, we don't know what the goalposts look like. We need to look at doing better week by week, month by month, year by year. The industry that is driving autonomy, the research community, needs to look at the safety cultures that exist in aviation. Accidents that have occurred in the last few years, whether those are with Tesla's autopilot system or higher levels of automation, transition issues, and some of the reporting requirements in California or beyond are not acceptable in the safety culture that is needed. We need to look to building a trusted system. Only if consumers trust the technologies, whether that is as a rider or as a driver, will we see these technologies moving towards achieving their potential in the coming years. Policy leadership, as I mentioned earlier, to enable technology development. We're seeing a consolidation here among OEMs. MIT spin-off Autonomy, purchased by Aptiv, now in a joint venture with Hyundai, announced earlier this month. Strategic alignment in industry sectors with higher risk and billion-dollar investment is critical. But how do we motivate the public sector investments that are required? Paving roads effectively and building the connectivity infrastructure is federal trillion-dollar investments. Obviously, something that needs to be very well coordinated. So as we look forward here, I, for one, believe the future very well may be autonomous. In some sense, artificial general intelligence is the future. Some would believe it's just around the corner. I believe it's several decades, if not the best part of a century away. Significant changes in how we live and move will take decades and increased collaborative industry innovation. It's not a revolution of robots on our road. It's an evolution of robots. So we will continue to see higher level automated vehicles emerge in different technology improvements. But the key is evolving the business cases so decade-long investments can continue. Managing consumer expectations will be critical. When consumers are looking for technology that's impractical, they're not going to be happy with the practical. That means that they will not be moving to buy new vehicles quite as quickly and looking and unsatisfied with what they can ride in. Policy and industry collaboration is critical. Only if we have a vision forward that is synergistic can we maintain the billions of dollars of investment. It's all about connecting humans here. It is not about building a robotics logistics enterprise that humans are not involved in. We're about delivering packages and people to end users. Trust is critical. If I don't trust what's moving on around me, I'm not going to walk across the busy infrastructure. I'm not going to get in the vehicle. I'm not going to purchase it. I believe that for the foreseeable future, several decades, collaborative driving developments in the level 2 standard level, SAE levels, are going to be critical. As a savior to the automotive industry in revolutionizing how we move in vehicles that we own today. It's not that I see the traditional auto industry's model of consumer-owned vehicles as the distant future. It's just the practical realities. And we can innovate around those realities to build business cases for autonomy into vehicles today that assist the Uber driver, but don't aim to necessarily replace the Uber driver. And with that, I'm about nearly over my 30-minute quota. So I'd be happy to take any questions.
Brian, thank you very much. We do have a number of good questions. So the first one will be, one of the key barriers to getting autonomous systems into the hands of humans and used by humans is a matter of trust. So how do you go about defining the right behaviors in unstructured environments, proving that autonomous systems will consistently make the right decision and communicating those results in a way that's understandable by someone without a degree in engineering?
That's a really good question. And I think the first key is, and this is one of the key reasons that a number of years ago we started the Advanced Vehicle Technology Consortium, is you learn a lot by looking. And unless you understand the range and characteristics of how different individuals are touching technologies that are in production today, it is very difficult to innovate forward tomorrow. So outside of today's virtual world where we're all self-quarantined to different degrees, sit in the side of the road and watch vehicles move. The complex dance is amazing to think about. The complexities that we as drivers encounter, overcome. Building from that is critical. So the next move is beginning to test different changes, looking at the attentional models and building upon that and developing driver management systems to do it. And I believe that we can very much use and build technology to assist humans in making better decisions. And that's really the key. It's coupling the development of autonomy with the development of systems to help us make better decisions.
Another great question. To what extent will off-highway autonomy in markets such as agriculture, mining, construction be proving out first and then shape the rollout of the highway autonomy?
That's a great question. I think the developments in robotics and in mining, for instance, and agriculture are huge already. But it's all about the operational domain. So when you confine the operational domain to a mine or a farm field, you have less unpredictable events. And it's those unpredictable events that are going to be very difficult, or edge cases, as the technology industry would like to call them, that are going to, make it more difficult to take what works in a farm field for harvesting crops and moving that into production environments on the roadways that work no matter what the weather conditions are or no matter what the traffic complexities are. So I think very much investing in autonomy in these unique and specialized domains will captivate and teach us how to transition over the course of time.
A sort of philosophical questions, I guess. Why are we so wrong in predicting how long technology maturation takes?
That's an interesting philosophical question. Humans are really good at predicting the future. We are long terrible at timelines. And I think it's because we like to think we're futurists and we all like to think about the future. but we need to take a step back when it comes to business. We need to be realists at the same time. And I think, today's economy is a great, stimulus to sit back for a lot of corporate decision makers and say, okay, we need to take a fresh look at this problem. I'm not saying don't invest in the future, but how do we look and balance that with the realist projections of how do we change and enhance how we live our lives today? And, a lot of companies would like to say that we can invest everywhere. We can't. Long before coronavirus, there was always cost benefits of any decision. Where you put $1,000 of investment, well, it costs a different area. And we need to think about realistically what's going to have payoff in the business cycles that we see.
Next question. As we increase autonomy in vehicles and push to increase in trust in these functions, will this inadvertently affect future younger drivers by removing certain driver skills, such as checking mirrors for how quickly a vehicle approaching? What happened if there's a malfunction in the autonomy in a situation like this in the future, where we removed some of these basic driving skills?
So one slide that I didn't put in the deck today for time is that the future of driving is much more attuned to what we see as novice drivers today. We as drivers learn by doing. That means we learn to look at the mirrors, we learn to react to unpredictable events around us. As we drive less or assisted by automation less, it's no mystery we will cease to develop those skills. The aviation community has known this for a while. There have been bulletins by the FAA encouraging pilots to fly more to maintain skills. So the future risk on roads is much more synergistic with what we see as novice drivers today. And we see some of this already elegantly displayed in consumer vehicles. Kids are focused on their cell phones as opposed to the driving task. They're not learning. We need to reinvent driver education. It's nothing new. I have a couple articles from 5 or more years ago talking about this. We've known it. It just requires federal leadership, state leadership to rethink how we insure and license individuals to touch things in cars. So it is a huge problem, and it's a reason that there is a high probability that the risks on our roads increase over time as opposed to just decrease. If we're not thinking about this problem holistically, the risks will likely go up.
So I don't want to open up a can of worms, but we have several questions related to Tesla. For example, we already have some automated cars, for example, Tesla. How does the system influences other non-automated and automated cars?
So first of all, I encourage everybody online here to look at my Forbes blog, a couple pieces that I've written around Tesla. In one sense, Tesla's probably the most advanced autonomy system in wide deployment on the roads. On the other sense, it's probably one of the most irresponsible systems ever to be put on public roads, looking for drivers to supervise a highly automated system without any management support. So look, clearly Elon Musk has developed a system for collecting information, crowdsourcing information that is second to none. There is information coming back from every Tesla vehicle through the airways back into retraining and redeploying automation models it is truly remarkable. The hard part here is that we are setting a communication standard, and this is where my big problems come around, that Tesla is really providing a self-driving system. They are not. They are providing a fairly crude and brittle automated support system with a vision that they're going to fix all these problems tomorrow. It will take decades to fix the problems. Elon's been promising this for several years. These are very complex problems. I believe there is regulatory support needed. I believe that with deploying automation in level 2 consumer vehicles without strong camera-based driver monitoring is unethical and inappropriate. That's why you see the bulk of the responsible automotive industry moving to including driver management systems. GM is the leader there right now, but there are a number that I expect will be fast followers. So there are incredible advances that Tesla has made in the the deployment of highly automated technologies, but we as humans shouldn't be test guinea pigs on public roads. And that's where federal leadership is desperately needed.
Yeah, I'm glad we talked about Tesla. Brian, thank you so much. That was very illuminating. And now we're going to move to our next speaker, Luca Carlone. Professor Carlone is the Charles Star Draper Assistant Professor in the MIT Era Austro Department and a Principal Investigator in the Laboratory for Information and Decision Systems. His research interests include nonlinear estimation, numerical and distributed optimization, and probabilistic interference applied to sensing, perception, and decision-making in single and multi-robot systems. His work includes seminal results on certifiably correct algorithms for localization and mapping, as well as approaches for visual, inertial navigation, and distributed mapping. Today, Luca will speak on the topic of certifiable perception for high-integrity autonomous systems. Luca, over to you.
Thanks, Irina, for the nice introduction. Hi, everyone. It's a true pleasure to be here. It's a great honor to be part of the Autonomy 2020 event. And as Irina was mentioning, I'm Luca Carlone. I'm assistant professor in Astro at MIT, and I'm also principal investigator in Leeds and IDSS. At MIT, I founded the Spark Lab. Spark stands for Sensing, Perception, Autonomy, and Robot Kinetics. And my lab is working in the broad area of robotics and autonomous systems, but we have a specific focus on what we call perception, spatial perception for robotics. And today's talk is about certifiable perception for application that we all care about in autonomous systems, in particular high-integrity autonomous systems. So I think a good start for this talk is to tell you what I mean by spatial perception. And typically the one slide way of explaining spatial perception is for you to imagine that you have a self-driving car at some intersection. And you have to imagine that in order to navigate this intersection, your self-driving car needs to figure out where are the lane boundaries, obstacles, detect other vehicles, potentially track the speed of other vehicles, detect traffic signs, and potentially also reason over the future intention of the other vehicles. So these are all spatial perception problems. It's about essentially for the autonomous vehicle to figure out the external world. And put in a different way, spatial perception is the process of going from sensor data to an internal representation of the world. So here what you see on the left is essentially a picture of the camera image taken by the robot here. And on the right, you can see some internal model that the robot has of the external world. And of course, you can imagine that this world model is something that is crucial for the robot to make decisions and to decide where to move next. So simply put, spatial perception includes a number of challenges here, and I list just a few of them which are important for this presentation. Just challenges including object detection, localization and mapping, object tracking, among many, many others. One thing that is worth mentioning is that while for this presentation, I'm going to go back to self-driving cars a lot, spatial perception is a key capability for practically all robotics application. So if you think about domestic robotics and the Roomba, these will have some vision-based localization and mapping system, which is used to support navigation. So we'll have some onboard perception. Similarly, for application in factory automation, here I'm showing the Kiva system from Amazon Robotics, and many, many other applications, including infrastructure monitoring and search and rescue here. And one thing that is worth mentioning is that even applications that are not traditionally associated with robotics, such as virtual and augmented reality, there is actually no robot here, are indeed based on the same algorithm for spatial perception, which are produced by the robotics community. So the algorithms are essentially the same. So spatial perception is a key component of both self-driving cars as well as many, many robotics applications. And in the last few years, we have seen a huge amount of progress in this technology. So spatial perception has been deployed on a number of vehicles, both on the academic side and on the prototyping phase, as well as actual industrial products. So here I'm just showing 3 examples just for giving you just a visualization of what's going on. On the left, I'm showing an execution of a project that we've been working on together with JPL and Caltech, which is part of the DARPA Subterranean Challenge. So in this case, a robot, which in this case is the Boston Dynamics Spot, has to move in a completely unknown environment and build a 3D map of the environment in real time. So it has to sense and understand the environment in real time. And DARPA has been funding essentially this effort with the goal of doing search and rescue in underground environments, complex underground environments. So while this one on the left is more on the academic side and on the research side of things, in this meeting, of course, everybody will be aware that right now, like all major car manufacturers have been working on some sort of self-driving car technology, and perception capabilities are really at the core of these technologies for self-driving cars. And I'm putting another example here at the bottom right, which is the use of spatial perception for autonomous drones. And I'm providing an example from a pretty compelling startup, which is called Skydio, in which you should be able to see that essentially the drone is able to navigate in a completely unknown environment using onboard perception capabilities. And it's going, in this case, to track a human moving in the environment. So while it is worth stressing that there is a huge amount of progress being made on these technologies, a core message of this presentation is that there is still a huge gap between what robots are able to do right now and what is the capabilities, what is human perception instead. There is a large gap between robot perception and human perception. And in this presentation, I'm going to touch upon two main aspects. The first one is robustness for high integrity autonomous systems, which I'm sure everybody in this event will essentially pay attention to. And the second one, which is a little bit, I will need to explain what I mean by that, is about high-level understanding. Okay, so I will structure the presentation in these two parts, starting from the robustness for high-integrity autonomous systems. So why do we care about robustness for high-integrity autonomous systems? Well, it turns out that perception, as I mentioned, is a key capability for autonomous vehicles, including self-driving cars. And we have to realize that these applications are essentially high-integrity applications in which failure of perception system often have catastrophic consequences on human life. So this is an example everybody will be familiar with. In March 2018, self-driving Uber vehicle failed to detect a pedestrian and provided timely warning to the emergency driver, killing a woman in Arizona. And there are a few other examples which have been mentioned also in the previous presentation. For example, the Tesla Model S here, I think still in 2018, crashing against a concrete separator because essentially the vision system misclassified this concrete obstacle for a lane and decided to turn into it. So we have to realize that failures here of algorithms for perception have really dramatic consequences. This is why we're talking about high integrity applications. And to figure out one more example, to provide one more example, this is one instance that right now is getting pretty popular in the bottom right of the slide, which many of you will be familiar with. So the basic idea here is that if you use a neural network to classify a stop sign in nominal conditions, everything will work well. But if you put carefully placed markers, this one in black and white on the stop sign, essentially you can mislead the neural network to classify these as a 45 mile per hour speed limit, which is a pretty bad mistake to do at an intersection. Okay, so essentially we realize that as humans, we will never be tricked by these markers, right? So there is still a huge gap between what robots are capable of doing and what is human perception. And the issue with that is that failures in algorithms have catastrophic consequences. So the first message that I want to send in this presentation is that high integrity autonomy application require the design of certifiable perception algorithms. And I will be a little bit more concrete about what I mean by certifiable in the next few slides. In particular, I'm going to consider a specific case study, which is object detection and pose estimation. And here I'm providing a bunch of references to a more technical presentation in case you're interested, just for the sake of making sure that everybody's on board. When I'm talking about pose, I mean position and orientation. So for example, if you care about detecting another car, we care about detecting the car and estimating also the location of the car in 3D. So let me tell you about certifiable perception algorithms, and I have to do a disclaimer before starting. So in this presentation, I'm not going to talk about system certification. So as you know, there is a huge amount of attention on how to certify vehicles, both in terms of self-driving cars, which is in the case for 21448, or also like the traditional certification process for aerospace. So in this presentation, I'm going to tie back to system certification, but the focus will not be on talking about system certification, but it's going to be about certifiable algorithms. So what I'm interested in is to deal with algorithms, to consider algorithms which are important for self-driving, and essentially establish properties connecting the input to the output of these algorithms. And I'm going to briefly mention at the end how this ties back to system certification. So to ground the discussion here, I'm going to consider a specific application, as I mentioned, to object detection and pose estimation. And there are mainly, we can just broadly classify approaches for object detection and pose estimation in two categories. The first set of approaches is what is called end-to-end learning. And the way you have to imagine it is that my self-driving car is collecting camera images. And I want to detect, for example, an object in this image. The end-to-end approach is about feeding this camera image into typically a deep neural network and getting one-shot prediction of where the object is in the image. So in this case, you get either a 2D or a 3D bounding box defining where the object is in the image, which you can use to make decisions such as avoiding the car, following the car, or things like that. So this approach is fairly popular right now in computer vision and robotics, but has two main issues. So the issue number one is that this is mostly based on deep neural networks, and we all know that deep neural networks can fail in really unexpected ways, simply because if you're using deep neural networks outside the training regime, we can get very bad and weird failures. And I'm showing an example here, just a funny example. This is not even with a deep neural network, it's with more basic classifier, but the message is that typically in machine learning, you have to be careful about the mismatch between training and testing. And if there is a mismatch between the training data that you used and the situation in which you are testing your algorithms, you can get very bad failure modes. There is also a huge literature on computer vision about how to artificially create adversarial attacks. And here I'm showing two examples from the recent literature in which the one on the bottom is essentially how to add patterns on top of a stop sign to induce a neural network to misclassify the neural network, in this case for a sports ball. So it is an example similar to the one I was making in the previous slide. And this is how to trick a neural network essentially to classify and to incorrectly track a car, which in this case is stationary, but the neural network is tricked to believe that the car is moving in the lane, actually. So again, because of mismatch between training and testing, or because of adversarial attacks, deep learning can fail in really unexpected ways, and this should be no surprise to people working in self-driving and dealing with the neural networks. The second issue is somehow as bad as the first issue, which is these failure modes are not easy to detect. If I provide you a bounding box and I tell you, is this bounding box correct or not, it's not easy to design an algorithm which is saying this bounding box is wrong or not. So this is definitely not the landscape you expect. This is certainly not a certifiable setup, because our algorithms are likely to fail and failures are not easy to detect. So that's the opposite of being certifiable. So for this reason, I'm moving to the second class of approaches for object detection and pose estimation, for which there is a little bit more hope. So the second approach is an approach which is hybrid and combines learning with some geometric insight. As before, we have some input image, and we have to do object detection and pose estimation for the object in the image, in this case, a car. This second approach works in two phases. The first phase is about feeding the image to a feature detection block and extracting a number of features. So you can see here that rather than looking at the image, the whole image, we extract a number of features which you can think about as relevant points on the car. So for example, you can extract as relevant features the corner of the windshield, or you can detect the headlight as relevant features, or the wheels, okay? And one thing that I want to point out is that this feature detection has been a huge literature on what is a feature detection, but in recent years, this is again a neural network. So we go back to the previous setup in which there is essentially some sort of understanding which is relying on learning. This is the first phase. After we detect relevant features in the image, there is a second phase which instead is based on geometry and is based on traditional estimation, which is trying to fit a 3D model. You can imagine that this is a CAD model of the car, and it's trying to fit a projection of this CAD model to the 2D points that are extracted in the image, such that I can essentially localize where the CAD model is in the image itself. And as soon as I localize the car in the image, essentially I know exactly where is the car, and I know in which direction it's pointing. What is the location of the car with respect to the image, to the camera image. So this seems nice. There is now a combination of learning and a combination of geometry here, but it comes again with some issues, right? So the first issue is that the one in the previous image has been like, the one in the previous slide has been like an ideal setup. What happens is that, again, if we do deep learning-based feature detection, deep learning can fail again in unexpected ways. But here the failure mode are a bit different, because the failure means that in the feature extraction process, we get a number of features which are reliable, right? We detect the wheel, we detect the headlights, so we have a number of features in green which are good features to use. But at the same time, the deep network can be confused and can detect a number of features which do not actually belong to the car, so are misplaced, and I'm labeling these in red. So this is a first failure mode. And of course, if you do not tackle this failure mode, what happens is that you try to fit your model using standard estimation, and you get a very poor estimate of the position of the car, which is this one in yellow, which, as you see, does not really match where the car is in the image. So we get similar failure mode as the last, the previous case, which is approach number 1. But here there is a clear opportunity. So the clear opportunity is that if you're able to find the good points, the one in green, which I'm going to call inliers, essentially we can still find a good fit for the model. So if you're able to reject the red points, which are the outliers, we may still be able to get a good model as output. And at the same time, counting the number of inliers is telling us how well the deep network is performing in detecting features on the car. So intuitively, if I have many green points and few red points, the network is doing a pretty good job at detecting my car or features on my car. If instead I have many red points, probably the deep network is outside the training domain and is doing a poor job, okay? And by solving the second part, the second part of this sequence of operations, if I have a good algorithm to do robust model fitting, I can understand, the inliers from the outliers. So typically the second part, to get some robustness in the second part, people use what is called RANSAC, which is typical robust model fitting algorithm. And I want to start with motivation for why RANSAC is not enough. Towards this goal, I'm just going to show the failure rate of a standard RANSAC algorithm. So I'm showing in this plot as a number of as a function of the percentage of outliers, I'm going to show the probability of failure of RANSAC. Keep in mind that coming from aerospace, typically for safety critical applications, depending on the different aspects that you are dealing with, we look for a failure rate which is 1e-7, 1e-9. And here I'm showing the failure rate of a single block in the architecture. And you can realize that while things are fine when the number of outliers are low, like let's say less than 60%, there is a sharp increase in the failure rate for RANSAC in the regime in which there are high outliers. And in particular, the failure rate becomes larger than 1e-4 already when we are beyond 75% of outliers. So essentially, RANSAC has a failure rate which is incompatible with the one that you expect for safety critical applications. So for this reason, we try to say, okay, let's try to have a more grounded application approach for solving the model fitting side of things in this slide. Because essentially, if you're able to distinguish inliers from outliers, we can get very robust solution, and we can also detect failures on the deep learning side. I want to give you like a 2-slide overview. There will be just 2 equations, just to give you the flavor of the math which is involved in this approach. So you can imagine that a standard way to perform estimation to fit a model to the data is to minimize a sum of squares. So this is the so-called least squares approach. And here we want to estimate the x, which is the location of the car in 3D, such that the X is as consistent as possible with the data that I measure, the YI, and the data that I measure are simply this pixel observation, these features in the image, okay? And the R function is called the residual, is measuring the mismatch between a given X and the measurements that I'm given. So this is the most basic approach, and this unfortunately is not robust. So it's a least square approach, so that's why I'm putting like, just a quadratic function here. And the issue with that is that if you have outliers, this least square approach will produce a very poor estimate of the location of the car in your image. So what we did here is to take a step further and to say, can we consider a formulation for estimation which is robust to these outliers? And we look at the robust estimation literature to say that essentially an easy and standard way to extend estimation to be robust to outliers is to include binary variables theta, which can be 0 and 1. And this binary variable will be in charge of deciding whether a measurement is an outlier, red, or can be an inlier in green. And depending on whether the measurement is considered an inlier or an outlier, the optimization problem will try either to fit that measurement to the model or just to discard it right away. For those of you more on the mathematical side, you realize that essentially we replace the quadratic function, which is the least square cost function, with a truncated quadratic cost function. So what I'm saying is that if we can solve this formulation to optimality, essentially we are guaranteed to find all the inliers and outliers, and we can use this information to get very robust estimates of the position of the car, of the location of the car in the image. Unfortunately, pretty early on, we got a very negative result on this direction. So we got an inapproximability result saying that outlier rejection, this type of problem that I'm showing here at the top, is inapproximable in the sense that there is no polynomial time, there is no fast algorithm that can compute even an approximate solution to this problem. So one way you can see it is that in the domain of all perception problem, in the domain of all potential images that the car can collect, there is a subset of worst case problem for which no algorithm is able to, will be able to solve this set of problems. So this is pretty bad news. There is no way we can solve this outlier robust estimation in general. And rather than giving up, what we did is to propose really a new perspective on this problem, which is the idea of certifiable algorithms. A certifiable algorithm is essentially a fast algorithm that can perform well and can certify it performed well in common instances. Okay, so in typical images will perform well, but will declare failure and detect failure in worst case problems, which anyway are not solvable, in polynomial time. So there is no way we can solve them anyways. So in other words, we want to be able to solve all problem instances which are in green and certify that we got the right solution. And in the red box, we just want to detect that we got the worst case problem instance and declare failure instead of just returning an arbitrary estimate. So the first thing is that I would argue that it is the same thing is done by humans. As humans, if you're faced with a good image, you really understand what's going on in the image, or you're confident about your perception results. If you're provided with the worst case instance, rather than trying to resolve that instance, you realize that you cannot trust your perception. Essentially, you have to stop, which is pretty much the same thing that I'm proposing here. And as a byproduct of this idea of certifiable algorithms, we realize that actually in practice, the picture is more like this, in which the set of worst case problems is really tiny. The algorithms that we are proposing can pretty much solve all the problem instances they are provided. So in the interest of time, I will skip on the technical insight here. The technical insight is that we're using tools from optimization ranging from semi-definite to sum of squares relaxation, which are, again, telling us, trying to solve a problem, and they're either telling us I was able to solve the problem in the right way, or they just say I was not able to solve the problem. So this is kind of a confidence signal that the algorithm is able to send. Rather than spending time on the mathematical side, I want to give you a few instances here, like, of certifiable algorithms that we've been designing in the group in the last 2 or 3 years. So the first is about object detection in point clouds. So the problem here is pretty much the same as the one I was describing in the previous slides. I tell you that I want to detect an object, in this case a serial box, and I give you a bunch of scenes from in which I want to detect the object. And here you can see the result of the detection of the algorithm, which is able to correctly detect the object and estimates its pose in the face of a large number of outliers. You see that the outlier number ranges from 95 to 97 here, which is a setup in which traditional algorithms would fail. I'm providing a little bit more statistics on the bottom left of this slide. So here I'm showing rotation errors for the increasing number of outliers. And since these are errors, the lower the plot, essentially the figure, the better is the algorithm. And here you can see that the proposed algorithm, which is the one in blue, is called teaser, is essentially able to ensure the lowest error across all the other applications, all the other approaches. And the second best approach, which is the one in green, actually runs in exponential time. So it's not very practical for common use. To convince you that this setup is actually pretty challenging, I'm considering also a very toy example in which I consider a standard dataset, which is called the Stanford Bunny. And here in red, you see that I'm taking the Stanford Bunny, I'm downsampling the Stanford Bunny, adding a clutter in the scene. In particular, 80% of the points in this plot are completely off, so they are outliers. And you realize that as a human, you can try to stare at this image, but you cannot really see where is the bunny. Like the average human will not be able to see where is the bunny. Instead, if we feed this problem to our algorithm, the algorithm will be confident in saying, this is where I detected the bunny. And I want to remind you that this setup with 80% outliers is actually pretty easy for our algorithm, which can go up to 95, 99% of outliers. So we design algorithms to do also object detection in images, RGB images. And here I'm showing a comparison of failure modes for compare techniques, for essentially baseline techniques, comparing with the proposed method. And you can see that related techniques essentially can fail to detect the car. So this technique is saying that the one in yellow is where the car is in the image, which as a human you can see that is clearly incorrect. Ransack, which is an algorithm that I mentioned before, can kind of guess where the car is, but is still failing to detect the exact pose of the car. And instead, the proposed approach is doing a very good job here. And here, again, I'm showing like more statistics, but the bottom line is always the same. For increasing outlier rates, the algorithms that we are proposing are just more robust, more resilient to failures of outliers created by deep learning methods. So one more example here, I'm showing essentially three techniques. Shape, Sharp is the proposed approach, and these other two are competitors. And I'm showing the first row is about problems with 40% of outliers. And you can see that 40% of outliers, all techniques are doing okay. But if you go to a setup in which there are 70% of outliers, competitors are failing completely to detect where the car is. Instead, the proposed approach is doing a good job. Okay. So we can get just algorithms which are way more robust than the state of the art. And these algorithms are also able to say, I was able to correctly solve the problem, or I'm not sure if I actually solved the problem, which is really the notion of certifiability in a nutshell. More example, I will skip this in the interest of time. One thing that I want to mention is that I'm considering right now this idea of certifiable algorithms, but really the direction we are shooting for is to say essentially every autonomous system is just an interconnection of hardware and algorithms. So the basic question that I want to ask is how can we use these guarantees that we get, these certifiable algorithms, to essentially establish system-level guarantees which can support system-level certification for autonomous vehicles, okay? So how can we reason on interconnection of algorithms? So,
Luca, sorry, we just have a few minutes for questions. I just want to make sure because we have a lot of, if you want to finish the,
I was trying to finish at 30 and leave 5 minutes for questions.
Yep, go ahead. Okay,
so I will go fast. The second part is more something that I want to mention. Is a work in progress, but we are very excited about it. Is about the idea of enabling high-level understanding. And the insight here is that while the maps that I've shown so far are essentially point clouds or a map essentially defining the obstacle in the scene, for application in which the autonomous system has to interact with the external world and with humans, the system needs much higher level understanding of the environment. And in a nutshell, the message here is that true autonomy requires high level scene understanding, including both understanding of the geometry and understanding of the semantics, where the semantics essentially means object classes, presence of humans, rooms, and so on. And I want really to show just a single video about a case study, which is about real-time metric semantic mapping. So here we have been recently released open source, a library which is called Chimera, which is ensuring real-time metric semantic mapping on just an embedded computer. So the algorithm is essentially taking, the library is taking images, standard images, and a 2D segmentation of the images, such, similar to the one that you can get with deep learning, and is building a 3D map, which is both accounting for obstacles in the environment, but is also labeling the different objects in the environment with different colors. So for example, from this image, you will be able to see that the couch is in green, walls are in a different green, the ground is in gray. So you get really this rich understanding of the environment, similar to human level capabilities. And just before concluding, I want to mention that you are also shooting for even higher level understanding of the environment, similar to the one that humans can afford, in which not only we can reconstruct a metric semantic mesh of the environment, but we can also reason in terms of agents, objects in the environment, different places, for example, rooms, buildings, so a really hierarchical representation of the environment that can support decision-making and planning. And we're paying attention in particular to really heavily populated environments, which right now we're testing in photorealistic simulation like this one, okay? But you can imagine that this kind of technology will be readily usable also for self-driving application. So unfortunately, I will not have the time to go into the technical details of these. I will just conclude here by saying that spatial perception is a key ingredient for autonomy. Safety critical application really require robust perception. And we have been working over the last 2 years on the idea of certifiable algorithms as a practical approach to get robust performance. And we're also working on the idea that high-level understanding can really enable autonomy application and can be a way to really enhance robustness as well. And I want to finish this slide by thanking the students who are really doing the heavy lifting here, as well as the sponsor, funding these efforts, and to thank you for your attention.
Luca, thank you so much. We have a number of very interesting questions. So I'm going to start with this one. In mining, autonomy is dependent on detecting obstacles and collisions. LiDAR is the primary mode of localized navigation. How far away is solid-state LiDAR? Is the move towards more vision-based mapping of a local environment? And what advances have been made with mapping in poor environmental conditions, such as dust and snow?
Yeah, it's a good question. So actually the DARPA Subterranean Challenge, which is one of the efforts I mentioned during the presentation, is really targeting perception and mapping in really degraded conditions. And the conclusion, we are part of that. We actually just won one of the events in the competition, in the DARPA Challenge competition. One of the conclusions we had out of the competition is that sensor fusion, considering multiple sensors at the same time, is really a key aspect of robustness, because you cannot expect a sensor to work in all type of conditions. For example, if you have a camera, you have low visibility, the camera is not going to be reliable. If you have fog, for example, it's not going to be reliable. Instead, some type of LiDARs are better, like a radar is definitely penetrating fog. So essentially the idea is that by using redundant sensors, you can get more robustness. And there are a number of efforts which are more of on the technology side about developing LiDARs without moving parts, as the solid-state LiDAR that the question mentioned, which are definitely valuable because, of course, moving parts in a sensor are always sources of brittleness, essentially. So my take on this is that it is crucial to have multiple sensors. I don't believe that in the near term, we are going to be able to reliably use camera-only systems for true autonomous cars. So you can get really limited setup, like Tesla Autopilot, you can get very limited demonstration by doing camera-only navigation. But instead, for mapping, object detection, and so on, LiDAR is really like a key sensor to enable safety.
Okay. Many startups in the Boston area are addressing, let me just go here, are addressing robot perception challenge with particular reference to manufacturing industry, still compliance to human safety standards has to be addressed. Do you see certifiable perception as a possible solution?
Yes, I want to put this really in a nutshell. So when you're dealing with humans, you're dealing with safety critical applications. The numbers, the failure rate that you would like to see is similar to the one that you expect in aerospace. You expect 1 E-7, so that the failure rate is super low, is very unlikely, the system is very unlikely to fail. We expect 1 E-7, 1 E-9, and one of the insight, one of the messages underlying the presentation is that the algorithms that you're using right now will not get there. If you use algorithm like Ransack or algorithms which are typically used in computer vision, will not be able to get to that level of safety. And instead, with certifiable algorithms, we can definitely get to a much better shape in terms of failure rate. But there is this extra property, which is kind of nice, that in the unlikely case in which you have the algorithm is not behaving as desired, the algorithm will just tell you, rather than saying, this is my estimate, which can be potentially wrong, the algorithm is telling you, I'm not able to solve this problem, please stop the car. So I definitely believe that certifiable algorithms right now are, in my view, I really hope that will be a way to push the boundary of safety here, and will play a role, hopefully, in system-level certification. It's something that we are working on. I do not have final answers about that, but that's really the vision.
Luca, thank you so much. Unfortunately, we have to stop right here and move on to our final speaker for today, Professor John Leonard. John Leonard is a Samuel C. Collins Professor in the MIT Department of Mechanical Engineering and also a member of the MIT CSAIL. His research addresses the problems of navigation and mapping for autonomous mobile robots and underwater vehicles. From 2016 to 2018, Professor Leonard served as Vice President of Autonomous Driving Research at the Toyota Research Institute. There, Dr. Leonard has helped to lead an effort to create Toyota Guardian systems for increasing the safety of human driving by exploiting advanced perception and navigation capabilities developed by the mobile robotics research community. John, over to you.
Thanks, everyone, for this opportunity to speak. I'm really delighted to talk to you all. I'm going to tell you about my research in related to autonomy and navigation and self-driving. And so just to double check, you can all see my screen, right? I need to share my screen now, right? So we're going to share. Okay, great. I really feel honored to speak after Luca and Brian and Sertash. Those talks really kind of match a lot what I'm things that I'm going to try to talk about. So I really wish I had a lot more than a half an hour. I apologize for having too much material. There's just so much I'd love to say. So I want to talk about some of the challenges and opportunities in autonomy. And in my talk, something to kind of keep in mind, like if anyone's heard of Amara's Law, this is the, we tend to overestimate the effect of a technology in the short run and underestimate the effect in the long run. And I think that's very much the case with self-driving technology today. And so I'm an optimist in the long term, but I've been one of the bigger contrarians in the short term, along with Brian. And so for me, it's kind of a mixed emotions. Like I very much believe in this technology in the long term, and I want to do it to save lives and improve mobility for people. But I also think we need to be really cognizant of what the challenges are. So in my talk, I like to start with sort of self-driving cars in the news to try to give some context. Then I'll say a bit about my personal self-driving journey, some of the history and challenges of autonomous driving, and then some of the work we're doing at Toyota Research Institute, where I'm currently a technical advisor. And so self-driving cars in the news, in a talk with a real audience, I'd kind of ask you to raise your hands. Has anyone seen any news articles about self-driving cars lately? And I'm sure you have. But some recent articles, folks may have seen yesterday that the state of California approved Nuro's self-driving vehicles for public road operations. Nuro focuses on package delivery, and in their blog post here, which you can look up on Medium, they talk about how sort of COVID-19 gives a scenario where sort of contactless delivery could make sense. And so I think self-driving gives us a new way to think about moving people, goods, and services through the world. And it's obviously very timely. And you know, my heart goes out to everyone affected by COVID-19 as we struggle in this new normal. And I worry about the jobs impact. I'm on the task force for Work of the Future, and that's something maybe we could talk about in the Q&A. I believe more in human augmentation than human replacement as sort of a personal philosophy for AI and autonomy. Another notable news item going back a little bit further, in March, Waymo announced their first external funding round, which was reported to be $2.25 billion. Previously, Waymo, it's Google's self-driving car spin-off, they were only funded by Google. And this was a really big milestone in terms of showing, you know, the potential trajectory, but also maybe gives kind of thinking that it might take longer than folks were predicting for wide-scale deployment. If you go back to December, there was a sequence of strong media posts, including an article by The Verge, where one of their reporters was able to just take a drive in a Google car with no one in the driver's seat. And so this is one of these really amazing things that we're seeing happening. In Arizona, Waymo.
I'm about to go for a ride in one of Waymo's fully driverless cars here in Phoenix, Arizona.
So Waymo are giving fully driverless rides, empty driver's seat rides, which just to me partly is just kind of mind-blowing. But it shows how, at least in that operational design domain, they've really achieved a lot of maturity. And so they've taken Arizona Cardinal football players for 15-minute rides with no one in the car, Larry Fitzgerald. And someone posted this post on Instagram, which just kind of really blew me away. I don't know the full context for this, but it's a Waymo with no one in the car stopped at a school crosswalk. And that's a pretty amazing challenge, you know, in terms of deploying these vehicles loose in the wild. If you look, going back in time, sort of before the Uber fatality, there was tremendous hype in self-driving. And this captions sort of, in the past 5 years, autonomous driving has gone from maybe possible to definitely possible to inevitable to how did anyone ever think this wasn't inevitable? And this is where I would raise my hand and say, it's not inevitable, people. This is a really hard technology, and it's going to take a lot longer. So, so for me, my personal self-driving journey really starts with being a grad student in the late 80s at Oxford working on SLAM, coming to MIT to work on underwater vehicles, getting involved in the DARPA Challenge, where I was team leader with an amazing team of people. And then I was sort of a critic of self-driving on the sidelines, capturing driving data with dash cams in Boston and pointing out difficulties. But then since 2016, I've joined Toyota. Initially, I was on sabbatical. Now I'm just a day-week consultant. But with our approach, we call Guardian, which is one of the ways we think we can get this technology into the marketplace. So, so my background, I feel like I won the lottery in life in my career. I started working on the problem of SLAM, simultaneous localization and mapping, before it was called SLAM, and didn't get very far, but articulated some of the challenges. And this is a video from circa 12 years ago in the data center using stereo camera to build a map of an unknown environment. I came to MIT to do underwater vehicles, which is still a passion, and along the way got involved with self-driving and proud to be part of mechanical engineering and CSAIL at MIT. And so way back in time, this is a video of an early Sun workstation in our lab at Oxford, with the box next to it is a data cube. It's a $100,000 box that could just barely do frame grabbing, data acquisition, and edge detection at something like 3 to 5 frames a second. And so it was way too primitive back in the late 80s to try to do robot navigation with vision. I used sonar, ultrasonic sonar sensors on the robot that I used for my work. And we really want the competence of localization is the ability of a robot to know its position. And that's kind of the scaffolding on which higher level autonomy is built for mobile robots. And I came to MIT in 1991. I say I have truly found paradise, if there's any MIT alums that get that. And you know, the campus, I'm just so fortunate, and I miss MIT so badly, not having been on campus in nearly 4 weeks now. But my Mechie office is in building 3 here, where I'm moving my mouse and Stata, and we do tests down on the river with our autonomous surface robots and underwater robots. And I feel just so empowered to work with such amazing students and colleagues. And so I came to MIT to do underwater vehicles. This is a vehicle called the Remus, developed at Woods Hole Oceanographic Institution, one of my master's students on the right, Chris. And this is a vehicle called the Odyssey 2. I was involved with developing as a postdoc, which led to a spinoff called Bluefin. This picture on the right is an experiment we did with NATO, probably 15 years ago now, with Bluefin vehicles. And underwater, navigation is really hard because you don't have GPS, and you need to use acoustics to communicate and for positioning. The SLAM problem, you know, really it's to me, I think about the different challenges of different axes of how do we represent the environment? How do we perform inference? How do we build systems and make them autonomous? And so, you know, over the years, we've moved from different types of representations, metrical, topological, dense representations, things like Kinect fusion, TDS, truncated sign distance function, but moving increasingly towards objects and semantic mapping. So my research challenge is very much similar to Luca's in the sense of aiming for robust, lifelong autonomy, robots that can take the output of deep learning systems, but use them in a robust way. So we work on state estimation, data association learning, and we try to deploy robots in the ocean in various places and try to think about the challenges to get from the lab out into the real world. And so I had a lot of experience with underwater robots. We developed a mine hunting system for the Navy where we deployed small robots that could use a prior map made with expensive sensors deployed on a low-cost vehicle to navigate into a field of objects to try to find targets of interest. And we try to attack the SLAM problem in a sort of generic way where it would apply in many domains. And so, but my self-driving journey really came into force in 2006, 2007 when I joined with John Howe, my late colleague Seth Teller, Emilio Fritzoli for the 2007 DARPA Urban Challenge. And we had a pretty amazing team of students and postdocs, and shown here just a few little video clips. You know, this is Velodyne laser data driving up Mass Ave from MIT to Harvard. This is the ROT path planner that John Howe and his group and Emilio Fritzoli developed, and which the vehicle would build a local model of the world and then try to choose paths through that world that were safe and met mission objectives. And it was a very long story. We came in 4th place. I'll say a little bit more about that in a minute. But our team, if I look back in time, you know, really as faculty members, our product is our students and our postdocs and what they go on and do. And so, you know, this is Albert Wang, who's Sertash's co-founder with Optimus Ride. Ed Olson is a startup May Mobility. And to me, it was sort of like a Woodstock of robotics experience. You know, we were huddled in hotel rooms, having team meetings, working on like kind of decisions on code and planning and strategy. And, you know, anxiously watching when our vehicle was deployed, coming back, watching the data logs. And if you think about what's it take to build a self-driving car, the Urban Challenge is a good example. You have the sort of high-level navigation, sort of finding the waypoints, kind of where am I going? How should I get there through my route map at the sort of high symbolic level? Feeding a motion planner that tries to solve the tactical local navigation of what path should I choose to the world, going down to a low-level vehicle controller. And the sort of planning and control is on the left-hand side of this picture. The right-hand side has the perception and sensing, where we're taking sensor data from laser scanners, cameras, and radars, feeding it into try to build the local model we call the grid map of the world, which is where are the drivable surfaces, where are the lane markings, where are the obstacles, can we predict tracks for different vehicles? And it was just truly ambitious endeavor. In about a year and a half, our team wrote over 150,000 lines of code, deployed a robot in the world. We had the most sensors and computing of any robot in the competition. Seth insisted on this, having a blade cluster in the back, which at the time was a pretty ambitious computer. It had 10 blades, each with 4 processors, 4 cores, and it required 3.7 kilowatts of power when fully loaded. We used a 6 kilowatt RV genset in the back to power it, and a 2 kilowatt air conditioner on the roof to cool it. It was sort of a mobile supercomputer. And to make a long story short, Carnegie Mellon was 1st place, Stanford 2nd place, Virginia Tech 3rd place. We were 4th place, a pretty distant 4th place. We had a few incidents along the way, but we really tried out more of a perception-driven approach. We didn't want our robot to follow GPS blindly. And in fact, one of the key lessons of the DARPA challenge is that if you give the vehicle a really accurate a priori map, and the vehicle can localize itself very accurately with respect to that map, then it's easier to achieve sort of a more robust behavior because the vehicle knows its prediction, knows its position. It can make better predictions about what it should see. It kind of knows when something's going wrong or not. That's the approach that Carnegie Mellon and Stanford took. We thought that we were part of the mandate from DARPA originally was to do GPS denied navigation. So our vehicle was more tentative and cautious and sometimes got a little stuck because it was trying to navigate more based on its visual and LiDAR perception of the world than it is based on the prior map. And but if I go back to our team photo in terms of the legacy, so here's Ed Olson, who founded May Mobility, Certash, I'm extremely proud of, and Albert Wang, Emilio co-founded Autonomy, bought by Aptiv, and Carl Agnema. And next to Ed is, in shadow here, is Yoshi Kawada, one of our postdocs for the motion planning. He's one of the engineers at SpaceX that landed the booster rockets back on the barges and on the ground for Elon Musk for SpaceX. And myself and Luke Fletcher are working with Toyota now. And really the kind of legacy of this, it was kind of like, if you're in one of these DARPA challenge pictures, it's sort of like to the venture capitalists, these are like oil paintings, like there's something magical back at that time that people sort of brought that experience with them. And so there's Ed, David, and Albert back at the track. They created a completely new messaging, data logging, visualization system for our vehicle, something called LCM, which is being used now by a number of top startups and different programs. And so this is Optimus, Albert and Sertash's startup. May Mobility, Ed Olson's startup. The goal here for both of these companies is to do small electric vehicles at low speed that sort of complement public transportation and try to find a niche between robotaxis and public transportation. And they've quite a successful model for getting out in the world with experience sooner. So at this point, I want to sort of talk about some of the challenges. So historically, this was the DARPA challenge was in 2007. We had the economic crisis right afterwards, which badly affected the auto industry. But Google secretly acquired a lot of the top talent from the Carnegie Mellon and Stanford teams. So I recall in October of 2010, the Sunday New York Times broke the story, John Markoff, that Google cars were driving themselves autonomously in traffic. And I was kind of like this really wow moment to me. And at that point, they'd driven 140,000 miles autonomously. And the sort of, one day I think there are going to be Hollywood blockbuster movies made about this project. Sebastian Thrun, who's a leader in SLAM and many other things, Udacity, Anthony Lewandowski, who's been in the news a lot, and Chris Urmson, who left Google a few years ago to found Aurora with Sterling Anderson, an MIT grad. And to the Google founders, the self-driving car was this just amazing opportunity to change the world. They have obviously very deep pockets and they want to make a big impact. And the level of investment that they've made now over 10 years is truly stunning. I got the chance to ride in the Google Lexus prototype back in 2014. And I had to say, like I posted on Facebook, this was an amazing ride. I felt like I was on the beach at Kitty Hawk. It was really a flawless journey, about 20 minutes through the streets of Mountain View. And it's tantalizing that you feel like we're so close that when it works so well. And the potential upside or benefits, safety is a huge motivator. We have over 30,000 fatalities in the US due to traffic accidents per year. It's over 1 million worldwide. And beyond safety, you can think about these new models for moving people and goods through the world. So to the venture capitalists, the potential upside of this investment is kind of stunning. But there are challenges. And so I've been sort of one of the critics pointing out the technological challenges, and Brian mentioned a lot of these issues. Also the economic challenges, employment, ethics, the legal security aspects. There are a lot of difficult challenges. And so it's important to distinguish between the levels of automation and the approaches to autonomy. I'm assuming many of you have heard of level 2 automation, where 2 or more degrees of freedom are controlled. You have to be ready to take off at any moment instantaneously for a level 2 system. Tesla Autopilot's a good example. In level 3, which may or may not even exist in reality, the goal is that you would give the driver sufficient warning to re-engage in time for the handoff, maybe 10 or 15 seconds. But that requires a system with an introspective capability that it kind of knows when it's encountering difficulties. And then, and really in level 2 and 3, you can think about human has to guard the AI system, and people aren't bad at that for vigilance decrement reasons. And so Google chose to do level 4 and 5, where the human's only a passenger and perhaps in just a restricted operating design domain. And on the one hand, it's here today in Arizona, but on the other hand, to make it widespread, there are really big challenges. And so for me, back in 2013, I started collecting dash cam footage from Boston. This is one of my favorites near my house. This is actually a cell phone video taken by a 7th grader of making a left turn across traffic on a busy day. So there are cars coming. This is at rush hour in the morning. It was a bitter cold day, driving some kids to school. The cars from the left are coming pretty fast. There are occlusions, the tree, the mailbox. The cars from the right are backed up as far as you can see. And the way that I pulled out was that I waved at another driver and she kind of slowed and made a gap for me. And then I saw a gap and I went. And that's the kind of what social ballet of driving, the interacting with other people. That's really pretty challenging. Here's another example. This is Coolidge Corner in Brookline at night. A police officer is waving me to go through a red light. And at the next intersection, a police officer is going to raise their hand to stop me at a green light. And so if you think about interaction with traffic cops, police officers, this interaction with people, these are really, really hard problems. How would you create a deep learning AI system that could detect that that's a police officer and to kind of follow their instructions? This is the same intersection at a different time of the year when rush hour corresponds to the sun setting. And it's probably very hard to see, but this is the legs of a police officer standing in front of me. Here are the shadows from his legs. And so how do we deal with such situations when the sensing is so hard? And then, of course, difficult weather, snow, which, of course, reduces sensing range, maybe increases false measurements, but hurts traction. But an important critical thing is that these vehicles rely on very accurate maps to do their perception and locomotion. And if you cover the world with snow, you take away that ability to use a prior map. So this is from that Google system I wrote in 2014. They've released some videos saying how it works, and they use a prior map of the LiDAR reflectivity from the road surface to localize the vehicle down to a few centimeters accuracy. And that's just really hard. What happens if there's snow? So for me, there's sort of these big questions. How do you maintain maps, deal with adverse weather, interact with people, and achieve really robust computer vision? Ideally, we want perfect detection with no false alarms, which is really, really hard. And so for level 2 and level 3, the question of vigilance decrement is critical. Can we trust people to be ready to take control when necessary? And the research indicates that we can't. That's why Brian Reamer was mentioning the Cadillac Super Cruise system with its driver monitoring system. That's definitely the way to go. You want to be able to monitor the driver and interact with them. For level 4, we need this near perfect detection in a wide variety of settings, and that's just really, really hard. So at this point, I want to transition to my work with Toyota and our Guardian approach and to motivate it. And to me, it's just been this wonderful journey to be part of something. I was one of the first 6 people on the staff back in 2016 with Gil Pratt, Eric Krakov, and over Russ Tedrake. And then since then, we've grown to well over this number's a bit out of date now, but well over 300 employees. We've got locations in near Stanford, in Los Altos, near Michigan and Ann Arbor, and just close to MIT in Cambridge. And we're doing not just self-driving, but TRI is also doing robotics and AI for advanced material discovery and human augmentation. And this is probably almost a year and a half ago now, an all-hands picture from our garage in Michigan, where there's Gil Pratt, Kelly, our executive vice president, and Ryan Eustace is leading our driving effort. And we, it's amazing, so our approach is to try to create one autonomy system that can operate in these 2 radically different modes. So full self-driving we call Chauffeur, and it's what the code name was for Google's original project. And there the goal, level 4, it's fully autonomous driving engaged at all times. And this is probably going to happen over time, not for privately owned vehicles, but into shared mobility fleets. Whereas the Guardian is advanced driver assist kind of on steroids. So sort of like active safety, but using all the tools of autonomy. And so the goal is to build on similar hardware and software as Chauffeur, but to try to have the driver in charge. And instead of having the human guard the AI system, to have the AI system guard the human. So what's it take to build an autonomous driving system? Well, just very rapidly, the kind of components that look like a big group of people, but it takes a lot of people to work in this area. So the vehicle hardware, the vehicle software, safety and system engineering, mapping and localization, perception and prediction, planning and control. For our Guardian application with the driver monitoring and driver state prediction, we have something we call driver risk assessment. Machine learning is everywhere. Simulation is a really important tool. We take tons of data that gets fed to the cloud that we feed back into simulation and learning. Designing the user experience is really critical. And then you need vehicle operators that are highly trained for safety. And so just like a quick step through some of these teams, our vehicle hardware, Matt DiDonato is a DARPA challenge from the DARPA Robotics Challenge alum. Chris Welch next to him is an ocean engineering grad. I was very proud to be one of his mentors. So vehicle software is critical, safety, SLAM is everywhere, perception, using machine learnings to do segmentation and prediction, planning and control, how you develop advanced controllers that can operate with uncertainty, monitoring the driver state, using machine learning algorithms for better detectors. Simulation is critical in many forms, processing data in the cloud, UX, and then finally our vehicle ops. And actually our vehicle operators are some of my favorite people at TRI. They're really wonderful. They bring this great kind of experience, and the vehicle operators really have a great kind of role that's played. So with my remaining time, I just want to give you a little flavor of a couple things from, let's see, let me just check so with Guardian, the goal is to try to re-envision having a safety system that can take over with advanced robotic technology. And I'm just going to play a little video. This is a bit old now. It's from fall of 2017. This is a demo we did with a dual cockpit steering system. So we made a car with 2 steering wheels to let us test both these autonomy modes, Guardian Chauffeur. In this video, you're going to hear Gil Pratt narrating the video. Ryan Eustace is going to be driving in the right-hand drive on the passenger seat with our safety driver, Sharon, in the conventional US left-hand side of the seat.
Now we're going to demonstrate our Guardian system. We're going to emulate what happens when a driver falls asleep. Guardian can tell by using a camera that's part of the dashboard. The camera can even see through sunglasses in order to see what the driver's eyes are doing, or if their head is moving into a position that indicates they're not paying attention. So Ryan, whenever you're ready, why don't you go ahead and pretend to fall asleep. And now Guardian has stepped in, it's driving the car for you, and now it will offer at some point to give it back to you. Why don't you go ahead and take it now. One of the most frightening things that can happen on the highway is when a car in front of you switches lanes to avoid debris. You have very little time to react because your view is blocked by the car in front of you. We have sensors that can see significantly better than a human driver can see. The Guardian is going to take over where a car switches lanes in front of us in order to avoid debris. Here, that car switches lanes, Guardian decides we have to switch lanes also, and we avoid having a crash. Now Guardian has offered to hand back control, and Ryan has taken control back of the car. So today you've seen demonstrations of 2 basic technologies that the Toyota Research Institute is doing research on. This is all part of TRI's work to eventually build a car that can never be responsible for a crash, regardless of what the driver does.
So our dream is to build a car that's incapable of causing a crash. And this is from an article in October. We are working towards robotic vehicle demonstrations at the Olympics in Tokyo, which obviously, sadly, due to the COVID crisis, has been postponed. But this is one of our what we call Platform 4 vehicles, where we've moved towards this more sleek, integrated design with advanced luminar LiDAR sensors on the roof. And I could talk for an hour on this. We're a little bit, we're kind of a little bit under the radar screen in terms of various kind of publicity and so forth, but we do have, this is the Toyota Times in Japan. We have, there's a famous Japanese actor who visited us, and we can, with more time, I could show you a little bit more about some of what we're doing.
So Kagawa-san, I want to show you some of our test cars.
So this is one of our Platform 3 Guardian test vehicles. This car has 3 types of eyes: LiDAR, radar, and cameras. This car's brain is actually in the back of the car. This is where the car thinks and reasons about its world.
でもこれさ血管みたいだもんね。もう車は変わったな。
Want to go for a ride in these?
待ってたよその言葉を。
So if you're ready,
Yes.
we'll have you get in the car.
Okay.
Buckle
行き
up.
ます。
We're going to take you on a ride and teach you about the AI technology. So we'll show you the perception and the prediction and the planning that goes with it. This is the raw data that comes back from the LiDARs that are on the roof of this car.
100メートル以上のものを360度見ることができる。
見てんだ。
So,
Sorry,
I want to
for time, I better
show
not
you some of our test.
show too much of that. Sorry. Okay, so I'm going to conclude and take questions. I remain a contrarian for widespread self-driving in the very short term. I think there's an increasing realization that things that folks like Brian and I have been saying for a while, that this is a very hard problem. And there were some unrealistic timelines before. I think the key question is not when will they be ready, but where will they be ready? We can expect to see incremental deployment in limited areas. That's already here, say Channel, Arizona. I think infrastructure can make a huge difference. I'm a believer in V2V, V2I, sort of communications, smart intersections. You know, let's invest in cities and make them safer. But yet many fundamental research challenges remain to be investigated. In my MIT life, we're working on robust semantic SLAM in complex dynamic environments, the kind of things that Luca's working on. You know, I think there's very rich open problems there. How do you robustly couple perception to planning, achieving high integrity? And a whole other dimension, you know, we'd love to hire more and more faculty members in this area of how you interact with humans with AI systems, the sort of social ballet of driving. And I am an optimist for safer, highly automated driving, maybe more in a 10 to 20 year time frame in terms of how we can make cars safer. So, so at that point, I want to stop and take questions. And let me see how to do this here.
Yeah, John, I can just read you the questions.
Great, wonderful.
You want to do that. So let's see. The first question is, any thoughts on synergy with migration to vehicle and vehicle to infrastructure communications?
Yeah, I mean, I think at Toyota Research Institute, they've not made it a focus. It's something that, for example, my colleague Sanjay Sarma thinks about, some other colleagues at MIT. Toyota recently announced something called the Woven City, which is a vision for a futuristic city, which might have robots and self-driving and different kind of living spaces envisioned. I think that what we're missing is a good business model, an economic model that would let the private sector bring V2V, vehicle to infrastructure, V2I, in a way that kind of makes economic sense. For example, reducing insurance rates. We should have the technology now for like the left turn across traffic. Imagine if the cars were communicating to each other, how much easier that would be.
Yeah. Next question. Would like to learn your take on the deployment of V2I and V2V infrastructure within a geofenced area in order to move the technology towards removing the safety driver.
Sure. I think maybe that's a very sort of similar question in terms of, I think that if the challenge with V2V and V2I is who's going to pay for it. The government efforts, such as the CAMP program, they've kind of been a consortium of OEMs and they've made sort of good incremental progress, but it's sort of hard to extrapolate how do you make that widespread. So we're missing sort of entrepreneurs with a really good idea of how to do that infrastructure in a way that you know, that really pays for itself. Maybe cities will sort of adopt, you know, think of all the money that goes into painting lines on the road surface and all the sort of physical infrastructure. How do we create and maintain virtual infrastructure?
Okay, and maybe time for a few more questions. What is the current state of development for an accurate, low cost, less than 5K solid state inertial navigation system for an autonomous underwater vehicle?
Okay, so for underwater vehicles, that's a great question. I think typically for Doppler velocity logs and inertial systems, my best guess is you're still talking order of $100,000, $80,000, something like a FINS system, for very low cost underwater. We have a junior collaborator at Woods Hole Oceanographic Institution, Erin Fischel. She's working on cooperative acoustic navigation for underwater vehicles. I think that in terms of the self-contained, accurate, low cost inertial, you know, I think it's not going to be less than $5,000 for quite a while. That's one of the challenges.
Great. John, thank you so much. And thank you to all of our speakers today. This concludes our session, and I hope you found these presentations inspiring and relevant. Tomorrow's session will focus on platform technology for autonomy and will touch on such topics as 5G, measuring driver risk in the era of autonomous vehicles, and efficient computing for AI and robotics. The session will be hosted by my colleague, Ken Goldman. Stay safe and healthy, and goodbye.